minutes to learn about something about string theory. Okay, so let me pass to the chair of this, Ignacio Antonio.
Okay, so let's start for today. Good morning or good afternoon to everybody. So our first speaker will be Irene Valenzuela, who is going to give a review talk on Swampland.
Okay, so thank you very much for the introduction, and thank you to the organizers for putting together this conference in this difficult year and for the invitation to speak. So it's really an honor and a pleasure for me to give a review talk on the Swampland program at the String Conference. So I decided to focus on the progress that we have made in the past 2 years, since Matt Rees gave a Swampland review in Brussels 2 years ago. So I'm going to tell you what has changed since then, what we understand better, and what we still need to understand. And still, it has been very difficult to summarize everything of 2 years in 40 minutes, so I apologize already if I am missing something or not discussing other things in the detail they would deserve. Okay, so the big question that we try to answer with the Swampland program is what effective field theories at low energy that are weakly coupled to Einstein gravity are consistent at the quantum level. Okay, so they have a UV completion in quantum gravity. And the point is that not everything goes. And this is the same way that Leonardo started his review talk on Monday, that not every effective field theory, which is valid up to some cutoff, can be UV completed in a consistent theory of quantum gravity, unless it satisfies some additional constraints. So we say that those theories that look apparently consistent from a low energy perspective, but cannot be UV completed, belong to the Swampland, while those that can arise as low energy limits of a consistent theory of quantum gravity, like string theory, belong to the landscape. And the goal is to understand what distinguishes the landscape from the Swampland. So what are these constraints that the EFT has to satisfy from the low energy perspective, written in a low energy perspective language. Now, of course, this is a very ambitious and very important goal at the same time, because we are trying to understand what is the UV imprint of quantum gravity at low energies. And clearly, it's very hard to prove in complete generality any of these constraints because we don't have the framework to do so. But I think we can use all we have learned from string theory during all these years to try to identify patterns and try to gather as much evidence as we can for them from all the perspectives and techniques we can think of and we have developed during all this time. Because any small progress in this direction, I think it's huge because it's eventually trying to connect string theory and quantum gravity to the real world. So we have, following this spirit, we have some proposals that we call Swampland conjectures, and that are typically motivated by string theory and black hole physics. Now, this is a map of the conjectures that we had 2 years ago when Matt Rees gave the review. And let me not explain right now what they are exactly, it will become clear during the talk. But let me just remark that I have put in purple 3 of them, which we will see they are at the core of the Swampland program. And these years we've been gathering more evidence for them, understanding better, and also I think one of the most important developments is that there are emerging many relations among the conjectures that are suggesting that they are not independent, random statements, but they all seem to be connected and they might be just different phases of the same quantum gravity underlying principles that we are starting to uncover. So one of the goals is precisely try to understand these relations very well and see if we can use them to reduce the conjectures to the minimum number of statements that would reproduce everything. Okay. Okay, so how do we do that? So there is not a single approach. There are many different approaches you can take to try to gather evidence for these statements. And I think this slide represents very well the Swampland program in the sense that it's not just a bunch of people using the same techniques to study different problems, but it's more like a combination of different people with different backgrounds and using different techniques, trying to answer the same question. So I decided that instead of structuring my talk following the different conjectures as usual, I'm going to structure it following the different approaches that are used to gather evidence for the conjectures, so that I can explain you what we have learned in each case. So this is going to be my outline. I'm going to start with the topological operators and follow with string compactifications. And then I will discuss a bit ADS-CFT, positivity constraints, and black holes. Although most of the time will be dedicated to the first two, since it's where most of the work has been done. And I will finish discussing a bit the phenomenological implications. Okay, so let's start. So the first point about topological operators and cobordism is focused on understanding the absence of global symmetries in quantum gravity. Okay, so this is one of the oldest and I would say most widely accepted conjectures, meaning that any global symmetry must be broken or gates. And it has, even if it's an old conjecture, actually it has received a lot of attention in the past 2 years, because we have realized that it's more powerful and has more implication than what we thought some time ago. And this comes together because of this generalized notion of symmetries that give rise to a new zoo of symmetries to explore, and that has also triggered a lot of activity in the QFT community, as we will see next week. So my message here is that we can learn a lot, not only from the presence, but also from the absence of these symmetries. And one of the goals, for example, is try to understand what are the precise mechanisms by which quantum gravity avoids all these symmetries. So just to give you one example, we can reinterpret many familiar known physics in string theory as consequences of avoiding symmetries, global symmetries. So for example, systems of actions, Chern-Simons, localized degrees of freedom, branes dissolving on branes, and so on, can be understood as consequences of avoiding what we call these Chern-Weil global symmetries, whose currents are given by products of the gauge field strengths. And this might point out that maybe if the absence of global symmetries is something general of quantum gravity, all these top-down features could be more general as well. So here I'm talking about topological charges that involve gauge fields, but you could also wonder, what about topological charges that involve gravity? And there is a well-defined and precise notion to classify all these topological global charges based on cobordism classes. Okay, so precisely the idea of avoiding to have all these topological global charges is what led Jake and Cumrun to formulate this cobordism conjecture, which has received a lot of attention in the past 2 years. So the statement is that the cobordism group of a quantum gravity theory must be trivial, because otherwise non-trivial topological charges, cobordism classes, would correspond to different topological global charges that would give rise to a d minus k minus 1 for global symmetry, where d is the total dimension and k is the internal dimension of the compactification. Now, in order to explain how to understand this conjecture and this object, let me briefly first give the intuition of the geometric notion of the cobordism group. So basically, if you have two manifolds, they are on the same class, this cobordism, if their union is the boundary of another manifold 1 dimension more. Okay, so for example, then if you belong to the trivial class, it means that the manifold is a boundary by itself. Okay, so it can be string. Now, if we compactify string theory on these manifolds, the existence of this relation, of this cobordism, is a domain wall that interpolates between the two effective field theories that come from compactifying string theory on the two manifolds. And the case of the trivial class corresponds to an end of the world brane, where there is nothing behind. So the way to understand this conjecture is that all effective field theories, or theories of the same dimension, must be connected by finite energy domain walls. Okay, so that means that if you have some compactification of string theory and you compute what is the geometric cobordism group, and you obtain that is non-zero, it means, I mean, the way you should understand it is that it means that you are missing something, that you are missing some defect that would trivialize this coverdistant group, and that is necessary for quantum gravity consistency. So for example, if you have fluxes, this would tell you that you need to have branes and so on. And therefore, it can be used to predict the existence of new defects in string theory, which can even be non-supersymmetric. Okay, so this has been used in this quest of string universality to show that any FT consistent with quantum gravity arises from string theory, so that we can get everything that is consistent, which would be amazing, because then it means that the lessons that we get are not a matter of the lamppost. And there has been a lot of activity in the past years about this, trying to use Swampland constraints, anomaly cancellation, and a high level of supersymmetry to classify the possible EFTs and check if they have string theory embedding. And here I put some of the words, but let me, since Cumrun later on and so Mariana will discuss about this, and it will also appear in the discussion later on by Gary and Mirjam, let me not say more about this and continue with other topics. So I wanted to say one more thing about this coverdistant theory, which is an implication that has for the stability of our vacuum using bubbles of nothing. So a bubble of nothing is this non-perturbative stability, in which a bubble of nothing nucleates in space-time. And it's a perfectly smooth solution constructed by Witten for the case of a circle, in which it's very important that a compact manifold can shrink to zero size at the wall of the bubble. So it was constructed for the cycle, but you can do it more generally. And the point is that this is allowed if the compact space can shrink to a point, which should already sound familiar to you, because that means that it's the boundary of another manifold. And as I told you, this is possible if our compact manifold belongs to the trivial class in Bordesine group. So the statement that the coverdistant group must vanish in quantum gravity implies that there is no topological obstruction to have bubbles of nothing. Of course, this is only at the topological level. Then one has to study whether it is energetically favorable for the bubble to expand, and this is related to whether it violates some energy condition at the level of the classical Lagrangian. And this something has to be studied more. We have constructed some examples in which, indeed, when supersymmetry is broken by the vacuum, even if it's not broken by the theory, this can happen. But it's interesting because it opens a new avenue to try to show this other conjecture, which claim that any non-supersymmetric vacuum should eventually decay. And that was motivated by different means. Okay, so this brings some correlation between the absence of global symmetries and this statement. And following this quest of unifying conjectures and reduce them to a few number of principles, there has also been work relating the completeness hypothesis and the absence of global symmetries, which I will tell you about next. Okay, so the completeness hypothesis is the statement that there are physical charge states for all possible charges of the Wedge group that are consistent with Dirac quantization. And the question I want to address here is whether this conjecture, which is also a very old conjecture, actually follows from the absence of global symmetry. So they are not independent statements. And this is a question that can be purely addressed from the low energy effective field theory perspective. And for that, it's useful to, instead of talking of global symmetries, to talk about topological operators that characterize the symmetries. And the notion of a complete spectrum gets translated to the statement that all charged operators can end. So just in Maxwell theory, to give an example, we have famous one-for global symmetry with characterized by this topological operator, where the current is just the field strength. And the charged operators are Wilson lines that can break if we have charged states in the theory, right? If we have electrons. But then if they can break, it means that we can unlink the topological operator, shrink it, and then we get a trivial action, which would be in contradiction. So the one-for global symmetry is broken. The operator cannot be topological anymore. And only if we have a complete spectrum, the one-for global symmetry gets fully broken. So you could wonder whether this is a general feature. Okay, so whether no topological operators, so no global symmetries, happen if and only if all extended object charge operators can end. So we have a complete spectrum. And this is true for continuous groups, but it's not true in general for discrete or disconnected groups. However, it seems it can be true if we allow for a more general notion of symmetry, in which we allow also for non-invertible topological operators. So here I'm just going to refer to Suhan review to explain what more detail what these non-invertible topological operators are. And let me simply point out that we've been able to prove this one-to-one correspondence in a number of cases. So for example, for discrete gauge theories in 3D TQFT, and also for the electric completeness of the charge electric spectrum for general compact gauge groups in any dimension, as long as they are only coupled to matter, and the analogous of twist vortices charged under the -2 form symmetries. Okay, so the lesson that we can extract from all this is that I think we are in the process of understanding what is precisely the notion of symmetry that is forbidden in quantum gravity. These results suggest that maybe no global symmetry should be replaced by no topological operators, or more generally, no covordism classes. And of course, we have to understand how to formulate this better and why this is the case. But intuitively, I think it can make sense because topology itself is dynamical in quantum gravity, so probably it doesn't make sense to have topological operators, whether they are invertible or non-invertible, and because they are not well defined. And this is something that actually connects with recent developments to prove the absence of global symmetries based on unitary black hole evaporation, because the relevance of topology change in quantum gravity has also been clear in the recent derivation of the unitary page curve. And in this paper, they argue that this also is going to forbid the absence of global symmetries. More concretely, one can see that they are violated by the replica wormholes using the derivation, or more generally by topology changing processes. Okay, so this is all I wanted to say about exact global symmetries. The next point is going to be string compactifications, but before that, let me make a brief comment, hopefully brief, about approximate global symmetries. So the next question that should come to your mind is, okay, maybe I accept there are no global symmetries in quantum gravity, but what about approximate ones? How approximate the symmetry can be? Can we quantify how close we can get to restoring the global symmetry? Because this can have a lot of implications for the effective field theories, if we can say how much we have to break them. And we can try to engineer some global symmetry by varying the parameters of the EFT. So this corresponds to moving in the modular space. And then, I mean, how quantum gravity fixes this is because it pushes these points in which a global symmetry is restored to be at infinite distance. Okay, and then when we approach the points, the EFT breaks down in a continuous way, meaning that the UV cutoff goes to 0. Okay. Now, how exactly goes to 0 and what is the physics that forces this can be, for example, quantified by these other important conjectures, which are the distance and the weak gravity conjecture. So since I will talk a lot about them, let me define what they are now. So the distance conjecture is the statement that in general, when we approach these infinite distance boundaries in the modular space, we get an infinite hour of a state that becomes exponentially light in terms of the geodesic distance. So indeed, the UV cutoff goes to 0 because we cannot have infinitely many fields weakly coupled to Einstein gravity. And this implies an upper bound on the field range for an effective field theory that an effective field theory can accommodate with when it has a finite cutoff. Okay. So we'll see one of the most important open questions here is exactly what is this exponential rate, and I will show you the progress that we have made in this regard. Now, the weak gravity conjecture says that given a gauge theory, there must exist an electrically charged state with a charge to mass ratio bigger than the value of the extremal black hole in that theory. So this is again another one factor that can be determined from EFT data. And here the question is, what is the state that satisfies the gravity conjecture? So in this sense, there is a strong version motivated by string theory and modular invariance of the CFT2 that claims that there is not just one, but there are actually infinitely many states, so that they form a sublattice or a tower of states that satisfy the gravity conjecture. And here then the connection with global symmetries is even more clear, because we can send the gauge coupling of a theory to 0. Okay, so this charge is the physical charge that depends on the gauge coupling. And this is going to be at infinite distance because it restores a global symmetry, a U1 global symmetry. And then according to the good gravity, the cutoff of the theory goes to 0, and we again get this infinite tower of states becoming light. So of course, the weak gravity conjecture is valid beyond weak coupling, and it's also associated to black hole physics and so on. But let me now focus just on these asymptotic regions, because all these conjectures, what are telling us is that these, to have approximate global symmetries, weakly coupled gauge theories, large field ranges, all these things come at a price. Okay, and it's precisely in these corners where they predict the existence of new light states that can have an effect on the EFT and imply that the UV cutoff should go to 0. And in these towers, as I said, can have an effect and can be behind many of the universal patterns that we observe for the effective field theories that emerge at the asymptotic limits in the modular space. And here I'm talking about any limit in the modular space, not just small string coupling. Okay, this is not just about perturbative string theory. Okay, so this understanding better these universal patterns that appear and the relation to the towers is what has given rise to many of the relations among the Swampland conjectures. Okay, so that this with gravity and distance constrain the spectra, and this, for example, can have implications on the scalar potential, as we'll see. Okay, so then let me go to the next point of string compactification. So these ideas are very nice, but we have to try to check it. Especially, it's very useful to check these asymptotic limits to take string theory compactifications, because there, even if we lose some universality, we can provide quantitative and rigorous tests of the conjectures, which can sharpen them and fix all these order 1 factors, so that at least we can be confident of what is the precise statement that is realized in large classes of compactifications. So just for example, we can provide a lower bound for the exponential rate of these towers, which is valid for any Calabi-Yau manifold, any Calabi-Yau 3-fold. Okay, and not only that, but we also understand the meaning of these numbers. So in the end, there are very few possibilities that are allowed, which are fixed by the discrete symmetries, the discrete monodromy symmetry that characterize the different limits. Now, understanding these, like checking these conjectures in string theory, has also been useful to uncover new universal geometric properties of the compactification manifolds that were not known or that were conjectured by mathematicians by different means. So here I have some examples, like, for example, it has triggered a systematic classification of the infinite distance singularities in Calabi-Yau manifolds using mixed structures, which is also something very active right now in mathematics. And it's very useful to not just to classify the limits, but also to understand the physics around the limits, which has triggered this proposal of modular space holography, in which one tries to recover the geometry deeper in the modular space from the information, from the discrete data that we have at the infinite distance boundaries. There are also beautiful connections between algebraic geometry of Calabi-Yaus and modular properties of quasi-Jacobi forms. And also by studying infinite flop chains in M theory and Calabi-Yau 3-fold, people show that the distance conjecture implies this previously formulated mathematical conjecture by Kawamata and Morrison. Okay, so most of the work, let me remark, that has been done in has been devoted to identify the towers of states that are becoming light at the infinite distance limit. So they provide a confirmation both for the distance and the good gravity conjecture. And here we have followed a very systematic approach in which there has been a lot of activity, especially for theories with 8 supercharges and the towers of PP states, because there it's non-trivial that the conjectures are satisfied. So it's interesting to understand how. And at the moment, we have a very complete and solid understanding, I would say, of what's going on in these theories. So in the past 2 years, the progress actually has been made in trying to reduce the level of supersymmetry. Okay, so for example, trying to understand what happens in 4D n equals 1. So since I said I'm going to focus on the past 2 years, then let me just say a few words about 4D n equals 1 theories. The goal is to understand them at the same level that we understand now the case of 8 supercharges. And at the moment, it seems that all examples point to the universal presence of a weakly coupled BPS actioning string that becomes tensionless at the infinite distance limit, which it means that we can map infinite distance limits with RG flowing points of the string, which allows for a bottom-up derivation of the distance conjecture if the string satisfies the gravity. Now, I don't have time to discuss these things in detail, but let me also point out that the string doesn't need to be the leading tower. There can be other towers becoming light, like for example, KK towers. But it seems that so far there is a very constrained correlation between these other towers and the string tension. So that the mass is proportional to an integral power of the string tension. And in all the examples so far, we only find 3 possible values. So it's also very constrained as in 4D n equals 2. And why we only get these 3 values, for me, it's still a mystery, actually. So this is consistent also with this refinement of the distance conjecture, claiming that every infinite distance limit should correspond either to the compactification or some string perturbative limit, in which we have some string becoming tensionless and weakly coupled. And it would be interesting to understand this further to see whether we can find other types of limits or other types of dualities, right? Because the tower is very linked to the existence of dualities at infinite distance limits. Okay, so the reason why we're also studying 4D n equals 1 is because we want to understand what happens with the distance conjecture in the presence of a scalar potential, so that we can use it for phenomenology. In particular, we want to understand whether the values of the potential also satisfy the distance conjecture, even if they are not geodesics from the UV perspective, but axion monodromy trajectories. And here, I mean, in principle, I can say that they should, because if we want the distance conjecture to be consistent at energy scale, because we can always integrate out the heavy modes and apply the conjecture in the IR pseudo-moduli space. So they should satisfy it, but then it's highly non-trivial because it means that the conjecture itself is putting constraints on the potentials that are consistent with quantum gravity, because not every trajectory should be allowed. And this is something that has to be checked and understand better. But at the moment, what we know is that they do satisfy the distance conjecture in the case of Calabi-Yau-Flash compactifications. Okay, and it would be nice to understand this more generally and other setups. Okay, so just to finish the string compactifications, I want to briefly mention a bit other Swampland related questions which are issues which are not settled yet, but have triggered, I mean, well, we have had a lot of activity because they are very important problems, and there is a lot of recent activity about them triggered by the Swampland conjectures. So the first one is the scale separation in ADS. So we have this ADS distance conjecture, which comes from generalizing the distance conjecture, not just moving in the modular space, but moving on the space of metric configurations connecting different Vafa. So if one takes this generalization, it means that one can see that the flat space limit is at infinite distance, so that there should be an infinite tower of states becoming light that scale with the cosmological constant, so that we cannot have pure ADS without some internal space or some origin of the tower. Now there is a strong version which bounds the exponent. This is like try to bound the exponent of the distance conjecture of the tower, which would mean that there is no square separation in ADS between the external and internal dimensions. Now, this has triggered research in string constructions, trying to find counterexample of this, and revisiting in particular this model of the Wolf et al., which is these are potential counterexample coming from massive type 2A, which are counterexample to the strong version. Okay, so the value of alpha, but not to the mild version. So they all have always the towers of states. And the question is, what is the exponent? Now they are potential counterexamples because the 10-dimensional uplift is not completely known in these cases. So it's not clear, but there has been recent developments this year, and so far the model survives. Now, for the case of the sitter, as you can imagine, there is also a lot of activity. There are two avenues you can take, two lines of research. One is to try to determine whether there is the sitter at parametric control near these infinite distance limits, because sometimes the best way to find something is to find out where it's not. And surprisingly, even if we don't have an example, it's not excluded. And it's not clear why we don't have one, like why we cannot have some de sitter at parametric control. So far it seems that there is always this universal behavior that we always get a runaway towards infinite distance, which is consistent with an asymptotic version of the de sitter conjecture that the potential satisfies this inequality. And it's kind of a generalized Dine-Seiber problem, but that is valid not just for perturbative string theory, but for any direction in the moduli space. Okay. So understanding this better has given rise to new no-goes for the sitter, and also works determining exactly what are these factors in the context of string theory. And as I said, trying to understand why we have this runaway. So in this direction, some proposals is that the runaway indeed can be shown to be a consequence of the towers of states that are becoming light. And also in 4n=1, one can map this to the fact that we can interpret the scalar potential as the charge of some membrane, and this membrane saturates the gravity conjecture. Okay, so the other avenue is to go beyond parametric control, and then we have the famous proposals of Kekeler-T and large volume scenario, where there has been recent progress, although there is no fully controlled global description yet. But we will have a full discussion about this tomorrow, so let me not say more, and simply finish this with a comment that, of course, one solution is that it might be that the sitter is forbidden asymptotically, but allowed deeper in the bulk. And then the question is, how metastable can it be? What is the lifetime? So I just want to briefly mention that in this direction, there is this Transplanckian censorship conjecture, which allows for the sitter deeper in the bulk as long as it is short-lived.
And you have 7 minutes.
Okay, fine. So then let's go, I think this to the next 3 points, which will be very quick in comparison, and finish with the phenomenological implications. So for ADS-CFT, yeah, I mean, I think the Swampland program is very similar in the spirit to all the conformal bootstrap approach. We are trying to determine what is the space of consistent theories. And there are many correlations between the two programs. I just want to remark some things of the past 2 years. So, I mean, one could expect, one can try to translate these Swampland conjectures to statement in the CFT so that they can be proven by different means. And for example, we have this CFT version of the distance conjecture, in which we basically connect this tree notion of infinite distance, free point, and higher spin towers. So we propose that at infinite distance in the conformal manifold, measured by the Samologikov metric, we always get a free CFT, it's a free point, and therefore there is a higher spin symmetry. Okay, so some of these directions can actually be proven in superconformal field theories, in the sense that if we get the higher spin tower, we can show that in superconformal field theories, we need to have free vectors, so the gauge capping, there's a gauge capping that goes to 0, and then indeed it's going to be at infinite distance. And one can show just by perturbation theory that the anomalous dimension, so how much it deviates from the unitarity bound, decays exponentially in terms of this distance. So it's the analogous of the distance conjecture. Now, when we have a weakly coupled ADS dual, indeed we can reproduce the distance conjecture and provide a strong version because we are specifying the spin, and we can also tell exactly, I compute what is the exponential rate, which in Planck units is going to be given by the ratio of the central charge and the dimension of the gauge group getting free. So it gives an interpretation of these exponential rates in terms of what portion of the theory is getting free, right? Like you are trying to decouple things, and that has an effect. And it also gives a lower bound for alpha because the dimension of the gauge group cannot be bigger than the central charge. And let me recall that lower bounds is what we need to give upper bounds on the field edge. So this is if we have a weakly coupled dual, but actually the conjecture should be valid beyond Einstein gravity, which makes me wonder also to what extent some of the Swampland conjectures, even if they are originally formulated for weakly coupled theories, sometimes might hint deeper principles of quantum gravity. And here I just wanted to mention other works of testing the weak gravity for non-holographic CFTs. Okay, so this is ADS CFT. Let me then quickly say a few words about positivity constraints and black holes. So for positivity constraints, there are amazing new developments that we have seen in Leonardo's review about bounding higher derivative terms on EFT weakly coupled to gravity, which is also a way to quantify what is in the landscape and what is in the swampland. Now, since we already had a review, let me just add one more thing, which is that positivity constraints have also been used to try to prove some mild version of the weak gravity conjecture by studying higher derivative corrections to the black holes. So one can aim to show that these higher derivative corrections are positive using unitarity and causality, so that small black holes themselves would satisfy the weak gravity, and this is what we call the mild version. And there have been works, extended these works by adding scalar fields, and the conclusion is that unitarity and causality is not completely enough to show the weak gravity unless some additional mild QB structure is satisfied. But for example, this can be just assuming that there is an SL2C symmetry preserved by the higher derivative terms. Okay, and regarding black holes, there has also been works testing the weak gravity conjecture in black hole solution, especially adding scalar fields, because something interesting happens, which is that the super extremality condition that we use to define the weak gravity is different now than a repulsive force condition, in the sense that gravity acts weaker. So these were like the two interpretations of the weak gravity, and then one could get the impression that there are two different ways to define the conjecture. However, this difference actually disappears for extremal black holes or the towers of asymptotically massless states at the weak coupling limits. So this brings a nice interplay with the distance conjecture, because precisely because these two notions coincide, for these towers, we can use the black hole extremality bound to provide a bound on the exponential rate of the tower and fix these order 1 factors in the distance conjecture. And this is valid whenever there is a p-form gauge coupling vanishing at infinite distance, which happens so far in all the examples, and I personally believe that might be general. Okay, so this is all I wanted to say about the different approaches. I'm going to finish with the phenomenological implications, but before, let me just summarize quickly some of these ideas.
We have 3 minutes.
Okay, 3 minutes to summarize on the pheno implications. So we said that there are these 3 main conjectures from which many of the other things can be derived. We saw how this can be encoded in the notion of non-topological operators and endability. And from the weak gravity and the distance conjecture, there are also new ideas that have appeared, which I wouldn't call them new conjectures, but new generalizations or spin-offs coming from applying these conjectures in different setups. So let me take this as an opportunity to flash what are the other ideas and work that has been done that I didn't have time to discuss, and unfortunately I don't have time to discuss now in detail. But from the weak gravity conjecture, there are different ideas coming from thinking along the same lines of black hole physics or scalar fields, like trying to understand if there is a scalar version of the weak gravity conjecture, which can also be used to provide the exponential behavior of the distance conjecture. And for the case of the distance, there are also different works that have appeared, taking the same logic of requiring the presence of an infinite tower at infinite distance. But instead of thinking of modular space, thinking of distances in different spaces. And then there are also ideas regarding the jitter and the possible stability. Okay, so I'm gonna finish. I think I just need a couple of minutes for the phenomenological implications. So all this, I mean, it's nice and it's interesting by itself to understand what are the quantum gravity constraints. But I think the reason why we had so much activity on the Swampland program in the past years is also because of the potential phenomenological implications. Because we are giving constraints that can be used as new guiding principles to construct beyond standard model proposals, and can hopefully also bring new insights to solve the naturalness issues in our universe. So the point here is that not everything goes in string theory. We know that. We have to understand better what is possible or not. But if not the entire parameter space is consistent with quantum gravity, I think this means that we have to revisit the notion of fine-tuning and the logic of naturalness. So here this is just a list of the different works that have appeared in the past 2 years using the Swampland conjectures to constrain different models in inflation, dark energy, beyond standard model, naturalness issues. Of course, I'm not going to discuss all this. I just want to show you some pictorial diagram of what are the possible phenomenological implications coming from each of the conjectures. So clearly from the global symmetries, we can constrain models with very well approximate global symmetries. From the weak gravity, constrain models that have small gauge couplings or large axionic decay constants. From the distance conjecture, models with large field ranges. The jitter is clear. And then there are also works constraining the hierarchy problem and providing some insights into naturalness issues. So I find this very exciting because I think it's a very exciting possibility that quantum gravity can be behind all these naturalness issues. And it can change the logic of naturalness and the expectation of scale separation. And I'm going to finish, this is going to be my last slide. I want to finish remarking what we can tell about naturalness coming from the Swampland program, and just highlighting the works that have appeared in the past 2 years in this topic. So there are works that we can apply the jitter conjecture to constrain quark masses and the theta angle, and also give a bound on the electron hierarchy problem under certain assumptions. Also requiring that cycle compactifications of an EFT satisfy the Swampland conjectures. We get that in a SUSY broken EFT with 0 or positive cosmological constant and this condition in the supertrace, there must exist a surplus of light fermions with masses below the cosmological constant. So this applied to the standard model. It explains the numerical coincidence between neutrinos and the cosmological constant, and also implies that they should be Dirac unless there is some light fermion in dark matter. And finally, the Festina-Lente proposal, which I didn't have time to discuss, but it's like thinking along the lines of the weak gravity conjecture for black holes in the jitter. One derives that all charged particles must satisfy this inequality in terms of the gauge coupling and the Howell scale. So it also provides an explanation for the electron hierarchy problem. Now, all these are examples which break this logic of naturalness because they provide non-trivial correlations between the IR observables that seem unnatural from a low energy perspective. In particular, the last two relate the electron hierarchy problem and the cosmological constant problem. And of course, you should take all this with a grain of salt because they all have additional assumptions that we can hopefully discuss later in the discussion. So maybe they are just coincidences, but maybe not. And I think that these, at the very least, motivate us to understand this conjecture better and try to gather evidence for them from all the perspectives we can think of. Okay, so I'm gonna finish here with the same way that I started, because it's very important to consider many different approaches, because it's only when we get when using different approaches and different corners that assume different things, and we still get to the same ideas, that we start thinking only then that we start thinking that there is something behind, and hopefully eventually being able to apply these ideas to finally connect string theory to the real world. So thank you very much for your attention.
Thank you very much. Other questions? I see Tolga.
I don't hear anything.
Ivano Basil.
Oh, yeah, hi.
Hello.
Hi, Irene. So thank you very much for the very nice review. I have a question about a specific detail of the distance conjecture. Specifically, I was wondering, would you say it's only sensible to consider trajectories in field space such that each point in the trajectory corresponds to a physically possible web of the fields? I mean,
you mean a vacuum?
I'm sorry, what?
You mean a vacuum, like it's a possible
Essentially,
vacuum?
yeah. What I mean is, does each point have to be such that if the fields took that constant value everywhere, it would be a vacuum?
So, I mean, originally it's formulated by moving in the field space, so every point is a vacuum. But I think it can be more general than that. Like if there is a reason why we get these infinite towers at the end, we could try also to approach the point by discrete steps and get the tower in the end. So what is more difficult is how to formulate this distance in that case. Yeah. So we have to understand, I mean, the tower is decaying exponentially in terms of what exactly. Right. But if the presence of the tower is linked to what happens at the asymptotic limit, I think it should be independent of how we approach it.
Because, I mean, I guess it makes sense considering a recent paper of yours that if the fields are massive but still light compared to a relevant scale, you can think of a suitable pseudo-moduli space, right? But I was
exactly. I think that in physics grounds, whether it's exactly massless or just very light compared to the energy that's of the effective field theory, I mean, it shouldn't be such a drastic difference.
But I was wondering whether there's people that just consider any arbitrary trajectory in the space of fields and not necessarily backward.
Well, I think you have to be careful with that because every arbitrary trajectory is not going to give always the exponential behavior.
Right.
So
you Sandeep Trivedi was asking a question.
Thank you very much.
Thanks, Ignatius. But I just saw on the chat, Daniel had a question which I was going to ask. Maybe Daniel has his hand up. He can ask it. Otherwise, I can ask it later. Sorry, I think
I guess maybe Sandeep and I have the same question. So I was just a little bit surprised when you said that you think that asymptotic weakly coupled de Sitter solutions are not excluded. So I'm not an expert, but my impression was that they're pretty general theorems that at least morally exclude it. So can you elaborate on that?
Yeah, no, I mean, they're beautiful no-go theorems, but they always have some assumption. Like, for example, I mean, they are excluded in, like, depending what is the sources that you have, what are the types of brains and orientifers and so on. So even like the Maldacena-Núñez theorem, right? It depends, like, it doesn't work if you don't have supergravity ingredients like other type of orientifers and so on. And there are different no-goes, but again, they all depend on what ingredients you are putting in the compactification. So there is no general no-go for that.
But I mean, I would have thought to have a continuous parameter, you kind of need to have unbroken supersymmetry. Maybe that's incorrect, but and we know that you can't have unbroken supersymmetry in de Sitter.
But I mean, you can have some de Sitter vacuum and then go to zero. I mean, with the potential and the question. I mean, you can engineer. I can just engineer some scalar potential in which you have some metastable de Sitter vacuum.
But that still sounds isolated. I thought when you said asymptotic, I thought, to me, that means there's a family of de Sitter solutions that go off to some weak coupling limit.
I mean, that's
not what you meant.
No, I mean that it can happen at parametric control in the sense of in these near asymptotic regions. So
is KKLT an example of that?
No, KKLT is not, because it's not just about the perturbative potential. It's really, you really need a balance, right, between the non-perturbative and the perturbative effect. So you cannot push this vacuum to large values, I mean, to the asymptotic region.
When you say push, I think you mean there's a family, right?
There can be, I mean, okay, that depends on whether these continuous parameters that you are varying, like the fluxes and so on, you can just vary in such a way that you get a family because maybe they are not bounded by tadpole cancellation or things like that. I'm thinking more general terms. Maybe, I mean, depends. But if we are thinking of flash compactifications, yeah, it could be like a family.
Maybe I'll leave to Sandeep if he has any.
No, that's very helpful. So Irina, I mean, many of the old no-go theorems were within the context of, say, classical supergravity, even in the presence of
exactly,
and so on. And are you saying that they, of course, hold, but the window is not definitely shut?
Exactly. So they all are very nice and they all hold, but most of them, many are about classical supergravity. Many of them are also about weak string coupling or large volume, things like this. And there are many more asymptotic limits that you can take in the moduli space. Like we are thinking about the full moduli space in lower compactifications. It's not just everything about small string coupling and large volume. Like we can move to different corners in complex structure moduli space and other things. And there it's not, I mean, all these theorems based on perturbative supergravity are not valid. And still, when we do it, we get the same behavior. So it seems that there is something more general that is not associated to perturbative string coupling or a supergravity description that appears at every and any asymptotic limit of the moduli space.
I see. Even after dualities and so on, perhaps, huh? There are corners which you can't, okay.
I mean, one can always say that by dualities, everything will get connected, but I don't know, let's
Yeah. Okay, thank you. Thank you very much. Thank you.
I think we have to stop here because the time is over. So thank you again, Irene, for your talk.
Okay, thank you very much.
And our next speaker is Cumrun Vafa. He's going to talk on finiteness, compactness. There's a Swampland.
Yes, thank you to the organizers of this fantastic conference and these difficult times. I'm also grateful for their inviting me to give a talk here. I'm going to talk about certain themes which are loosely related, and in particular finiteness and compactness that has been seen in the string theory landscape and the relation to Swampland. So this is going to be based on a number of works with very good collaborators I've been lucky to work with, including Yuta Hamada, Uri Tarazi, Miguel Montero, Irene Valenzuela, Cody Long, and Alec Bedroya. Some of them already appeared and some of them are work in progress. So let me first give you a review for my talk. The plan is, first of all, I talk about finiteness of the string landscape, what evidence we have that the string landscape is finite. And then I focus about the perspective that we get from the Swampland conditions, what kind of reasons do we have for finiteness and theories with 16 supercharges, and talk about compactness of the brane probes and the relation of that to reconstructing of the internal geometry of the space as we see in string theory from the low energy effective field theory perspective. Finiteness in 6D is the next thing I will mention briefly, and then I move on to the so-called the desert scenario on the relation of the desert scenario with finiteness. So it has been long conjectured or believed that there are a finite number of known Minkowski, there are a finite number of known Minkowski vacuum, but there are also believed that there are a finite number period because in particular, an example of it being the convex of Calabi-Yau. For example, it's believed that the number of Calabi-Yau manifolds of a given dimension are believed to be finite. We don't have a proof of this, but it's conjecture. Of course, this should not be confused with what we see in the context of ADS-CFT. We, of course, have infinitely many defects in a given theory. For example, in type 2B, you can have 3 branes, an arbitrary number of them you can put parallel to each other and go to the low energy limit of that and get the so-called the description of ADS-CFT in terms of the relation to these D3 branes. There are infinitely many ends you can choose, and for the, of course, in 10D, that's not, so the infinity has nothing to do with that. The finiteness refers here to the theory in the bulk, And this is also related to the fact that if you want to have ADS, you will always end up with these extra degrees of freedom, which is this fact that there's 6 extra dimensions in the context of D3 brane. This is related to the de Sitter conjecture, ADS conjecture that Irene mentioned, and the Tower of Light states. So let me focus mainly here on the finiteness in the context of the Minkowski vacuum. And the examples we know in string theory, there are plenty, but let's just review some simple ones with a higher number of supersymmetry. A theory with 16 supercharges in d dimensions in the string landscape has a bound, at least in all the known examples we know how to construct, for the group that appears, which basically defines the theory. The rank of the group is less than or equal to 26 minus d. And a theory with 8 supercharges in 6d has, in fact, a provably finite construction from F theory, because there's actually now a proof that there are a finite number of elliptic Calabi threefolds. And so therefore, if you use any of them, you only get a finite number of choices. So these examples and many more suggest that for any consistent theory of quantum gravity in any dimension, there is an upper bound on the number of massless modes, which may depend on the dimension and the number of supersymmetries. So this suggests a lucky situation, a lucky feature for us, that the landscape of consistent quantum gravity theories is finite. So this is what I refer to as a finiteness conjecture. So let's start with what we can say from the bottom up, from the effective field theory perspective now. Well, if you start with the highest amount of supersymmetry with 32 supercharges, the massless modes are determined by supersymmetry alone and is unique. So at least the matter content is fixed. And in this case, there's this finite, there's just one unique choice. So that's trivially satisfied at the level of at least of massless field. Of course, one could imagine a theory where you have the same massless field line, but infinitely many different UV completions of it, but I'm not going to be discussing that. I'm going to focus only on the massless modes. Theories with 16 supercharges, the chiral versions of 6C and 10D are essentially fixed by anomalies. 16 supercharges have different versions with or without chirality. In 6C and 10D, for example, we get chiral versions. And those are fixed by anomalies and they're finite. Therefore, one can check explicitly they are finite, there are not many choices. For non-chiral versions, using a stronger version of the completeness hypothesis, in this context applied to strings, to the fact that there's a two-form gauge field, and using the strong form of the distance conjecture, it has been argued that the rank of the group should be less than or equal to 26 minus t, which is what we have seen in the string landscape. I briefly talked about this in my strings talk last year. In particular, I focused on dimensions, high dimensions with 16 charges, 16 supersymmetries, dimensions 7, 8, and 9. So the upper bound of 26 minus t is what is denoted here by these red lines. Here, 17, 18, and 19 are the upper bounds that you get in string landscape. But actually, the ones that you do see in string landscape are given by the ranks denoted here by the green squares. Not every rank that is less than those numbers appear. The yellow ones are the ones, the yellow and the green ones are the ones which are consistent with anomalies, some discrete anomalies. And still, you see that you don't get all of those. You only get very specific subset given by these green ones. And the rank restriction in dimension 9 and 8 has been related to covariance conjecture, and this one I talked about last year. And as I mentioned there in the dimension 7, the fact that you get the parity correct, these green ones, is explained, but not all of why don't you get these other ranks. So we have some amount of success in describing what we actually see in the string landscape from Swampland ideas. But in fact, there are more to be said here because not all combinations of gauge groups with the correct rank appear. It's not enough to say, well, you have a theory with rank 17, just choose any gauge group you want, which adds up to that rank. Not all of them appear. So at least they don't appear in string landscape. Is that the reason for them, or there are other constructions that we're missing? Can we explain this? So the Swampland bounds up to now had focused mainly on unitarity of string probes. And the basic new ingredient that we want to consider is the magnetic version of these strings. So for example, in 8 dimensions, the magnetic version of a string is a 3-brane. Gauge group instantons, if you have an gauge symmetry in 8 dimensions, instantons lead to a 3-brane charge due to their coupling. So you can view these 3 branes as related to the instantons. And these preserve half of the supersymmetry, leading to a theory in 4D, and namely on the 3-brane probe, which has n equal to 2 supersymmetry in 4 dimensions. So, you have zero-size instanton or these brane probes, what we usually think about, but now we can think about it in terms of the effective 8D theory without reference to where we got this 8D theory from. Now we get a rank 1 Coulomb branch from studying these small instantons, and this gives you a Coulomb branch for these 4D n equal to 2 theories. And now we want to study what kind of Coulomb branches we get. And now I argue that this Coulomb branch should be compact based on black hole entropy arguments. So the black hole entropy arguments compactify, give you a reason why these Coulomb branches should be compact. So in fact, more generally, we argue that in a d-dimensional quantum theory of gravity, the moduli space of any p brane with p less than d minus 2 is compact. More precisely, the spectrum of the Laplacian on it is discrete. So the basic idea is to compactify the theory from d dimension on a, let's say, p-dimensional torus and wrap a p brane on it, leading to a black hole in d minus p dimensions by this. The eigenstates of Laplacian translate to states of black hole. Now we have the analog of a 0 brane in this lower dimensional theory. The number of states in a given mass range is given by the Bekenstein-Hawking formula. So you can compute how many states you're going to get. And eigenstates of Laplacian in a given range do correspond to a subset of these. And so it cannot be infinite. It cannot be more than the Bekenstein-Hawking bound. So therefore, we should get a limited number. And in particular, we cannot have a non-compact space. Otherwise, we get an infinite number of low energy modes like that, and that's impossible. So the moduli space of any brane in the quantum gravity is finite as long as the dimension is sufficiently small. So let me make a side remark. So if we could apply this argument to space-time filling branes, having compact moduli, this in effect would mean that the bulk scalar fields themselves, because you can view the bulk scalar fields as if they are scalars associated to some space-time filling brane, they should be morally compact. Indeed, this is the spirit of the distance conjecture, that any effective field theory has only a finite range of validity, and the larger distance you go, you get light states emerging exponentially like power emerging. And this fits with the idea of emergence of infinite distance in field space, as mentioned, as suggested by these authors, from finite compact spaces. In other words, the reason we are getting infinite distance is because we have infinite tower of light modes, and that's the only way this non-compactness can be evaded. Compactness can be evaded by these infinite tower. And in fact, one can compute one corrections to the field metric from this tower plus some mild assumptions to show that the mass of the tower decreases exponentially with distance and field space, as demanded by the distance conjecture. So let me go back now to the 8D case for 16 supercharges. As I was mentioning, we are focusing on 3 brane probes, which can be viewed as a Coulomb branch associated with the small instantons. Now, so this gives you a one-dimensional compact space, a one-dimensional space which should be compact, but if you consider coupling constant represented by an elliptic curve on over this moduli space, it's easy to use n equal to supersymmetry to show that this gives rise to a hyperkähler geometry. So you do automatically get out of this a 4-dimensional hyperkähler space. And so therefore, since it should be compact, we end up only with 2 possibilities. Either it's a 4-dimensional torus or K3. Now, it has to be K3 if we have any non-trivial gauge group. And that we can see that because you can study locally the structure of this Coulomb branch when you have any non-trivial gauge group. And therefore, we deduce that the moduli space of 3 brane better be K3. One can also envision a possibility of having disjoint unions of K3s, but this could be ruled out by a strong form of covariance conjecture. So So this is indeed consistent with what we know with an F-theory realization of these theories. In this context, the 3-brane is nothing but a D3 brane probing the internal F-theory compactification on elliptic K3. So we have thus reconstructed the internal string geometry from the perspective of IR effective theory. This is quite amusing because one would have thought that IR may not have information about the extra space, and we are not going to KK modes to discover what this is. But just the very fact that we know something about extra dimensional branes, properties of higher dimensional branes, in this case a 3-brane, leads us, together with supersymmetry and compactness, to a restricted possibility, in this case K3. So somehow it is surprising that low energy has access somehow to K3, which is what we know from string theory constructions. Of course, whether or not the KK modes of that K3 have anything to do with massive modes that can be seen in 8 dimensions is a different story. But at the very least, we are beginning to see that we can kind of, instead of the famous question, can you hear the shape of the drum, which is by the eigenvalues of Laplacian, or the KK modes, can you reconstruct the geometry? Here we see that by the brain probe, by studying the brain probes, we can possibly get an internal insight to the internal string compactifications. With a higher amount of supersymmetry, we can argue instead of K3, we get tori, and that's also consistent with what we know in string compactification. For maximal rank theories with 16 supercharges, for d bigger than 6, this argument reconstructs the observed gauge symmetries in the string landscape. So at least for the maximal rank, namely 26 minus d, we are done with getting all the gauge symmetries that string landscape sees. And this provides another strong evidence for the string lamppost principle, that all the consistent quantum gravities are constructed in string landscape. For the lower rank theories, this study provides additional restrictions on gauge groups that appear, but does not completely fix the allowed sets to the known example. So it would be good to find other ways to think about it to completely fix the gauge groups that we actually do observe in string landscape. For theories with lower supersymmetry, let me just say something about theories with 8 supercharges, like 4d n equal to 2, but let's start with let's just only talk about the simplest one of those, which is the first dimension this number of supersymmetry appears. This is in 6 dimensions with 1, 0 supersymmetry. In these cases, anomaly considerations greatly reduce the available possibilities for matter, but still allow for unbounded number of massless modes. It can be argued that at least all such cases belong to the Swampland by a careful study of unitarity properties of the BPS strings in such theories. Some work we recently finished with my student Huri. So again, it seems that we have a landscape with an upper bound on the number of massless modes. So this is further evidences for all these finiteness I was referring to. But why are we getting? What is the reason for this finiteness? What is the explanation of it? This will be related to what I would call the desert scenario. So one idea of trying to explain the finiteness conjecture is based on the species problem for black holes. The species problem is the following. If you suppose you have a number n of light modes, and suppose n is arbitrarily large, and if you consider the entropy of a fixed size, say Planck size or slightly bigger than the Planck size black hole, if you fix it, then the Bekenstein-Hawking entropy cannot account for all of these n's if n is arbitrarily large. So this is the species problem for the black hole. So one might use this to try to bound the n, for example, to try to argue for this finiteness. However, a proposal to avoid the species problem and get arbitrarily large n is based on noting that any effective theory has a cutoff that may depend on n. So in a quantum theory of gravity, we expect the cutoff scale to be, for the effective theory to be always, of course, less than the Planck scale. So we expect there to be a cutoff lambda less than 1 in Planck units. So the radius of all black holes that you can describe using this effective theory will have to satisfy that R is bigger than 1 over lambda, depending on what lambda is. Now, as long as the entropy, which goes like the area of the black hole, R to d minus 2, goes like the smallest you can have, which is lambda to the minus t plus 2, as long as this is bigger than n, you have avoided the problem of the species problem. In other words, if the cutoff is less than n to the minus 1 over d minus 2, this avoids the species problem, as was noted in this paper. So this lambda, the lambda being equal to n to the minus 1 over d minus 2, is called the species scale. So it seems like we cannot use the finiteness of n to try to have this black hole issue, to try to argue for finiteness of the black hole entropy, finiteness of the string vacuum. So at first sight, it appears that we do not have an argument for boundedness of n and finiteness of the landscape. However, if we can argue that lambda should be close to Planck scale for some other reason, that it cannot be too far from it, then we may have an argument. If we have some kind of an independent argument that lambda cannot be too small compared to the Planck scale, then we have an argument. But actually, lambda, the cutoff will depend on, for example, for supersymmetric theories where you have massless moduli, the lambda will depend on what web you choose for these massless moduli. So the question is whether or not you can, as you change this moduli, can you go to points where this lambda is very close to the Planck scale? Can you always find points on the moduli space of theories for which there is a lambda is close to Planck scale? In other words, do we always have a desert? Can we always go to a point in the moduli space which realizes the so-called desert scenario? This desert scenario has been, of course, noted in the context of standard, in the context of grand unifications and the standard model, where we talk about what lies between the energy scale we see in the standard model all the way up to grand unification scales and the Planck scale. So here we have, in the log of the mass scale here I'm drawing in Planck units, we have -3 is the gut scale, and -19 or something like that around that scale is the weak scale. And so this is more or less massless here. And the question is, are there any other states here? In other words, our description here, does it have a cutoff, or can we push the cutoff all the way up to some dot scale or what? So this is the so-called desert scenario, or the question of desert scenario. And the question in our context is whether or not you can realize this for any quantum theory of gravity where you can push all the not light states all the way up to very close to Planck scale, maybe order -1, -2, -3, near the Planck scale. Can you, in other words, you have all these tower of states which are massive, and can you always find the point on the moduli where the lightest ones that appear are close to the Planck scale? If this is the Planck scale. So how do we address this question? Well, this seems to be the case for all the theories realized in the string landscape with at least 16 supercharges. For example, heterotic string at self-dual moduli and string coupling over the 1 has this feature. You can push every state. In fact, more precisely, what we can, of course, measure or reliably compute in these cases will be BPS states. We can check the mass of all the BPS states or scales associated with them, all go to very close to the Planck scale. That's one example that we can actually push them all the way up. How about lower supersymmetry cases? This is a feature of too much higher supersymmetry. Let's go to the next case we can try to study with 8 supercharges. So in 61,0 theories, which is the first case we get 8 supercharges, we can study the following question. Again, I want to focus on BPS objects because that we can reliably compute the associated mass scale. Of course, it doesn't mean there are no other states which have other masses, but this is the only thing we can completely reliably compute, and presumably everything else decays to these guys in some form. So let me focus on BPS objects. In 61,0 theories, you have a whole variety of BPS strings. For example, in F theory, you have 3 branes which wrap around 2 cycles on the F theory base, and these give you string, and depending on which 2 cycle of the F theory base you choose. So what we did is that we examined 34,000 or 871 toric bases in the context of F theory compactification, and tried to go to the moduli on this F theory by going to the sizes of these spheres and so on, such that you can push the strings of the mass scale associated with these strings as much as possible close to the Planck to see how much you get it. Of course, sometimes you can shrink them. That's not what you want to do. You want to kind of make them all big, all these two cycles big, so that the tension of these strings are large, so you're as much as possible close to the Planck scale. The question is, did we succeed or not? So here I will show you the result of that experiment. So here, H11 is the number of these two cycles, or what's in the 6D language is going to be the number of tensor multiplets in the log scale. So here they go all the way up to around 100 or so. And in the upscale is the lambda, the cutoff that we get when we tune the corresponding moduli to get these tension as close as possible to the Planck scale. So we see that we more or less succeed to get it. However, there is some behavior that as we go into larger number of tensors, which is larger number of light degrees of freedom, larger n, so you can think of this like the analog of the n, you see that the actual, the lambda goes down. So in fact, you get a bigger gap. The biggest gap we got here was, the farthest we got to the Planck scale here was around minus 1.5, so not much by just one order of magnitude, slightly more than one order of magnitude, only away from Planck scale. And if you look at the species bound in this case, you find in the 5D, it goes like n to the minus quarter. And so it has a lower slope. So this is, of course, we don't have an a priori explanation of why this slope should be minus 0.7, but this already tells you that this slope cannot kind of continue, and it has to stop because then it will be lower than the species scale, which cannot be. In other words, this bound better be higher than the species bound, otherwise there will be contradiction with the black hole physics. And so that would say that H11, the number of tensors, should stop somewhere. And so that is at least a kind of a semi-qualitative explanation if we could understand this mild behavior of this cutoff with the scale. So this does not quite completely do the job for explaining finiteness, but it goes towards the idea that the issue of the black hole species problem might be related to this finiteness in some refined version. So I think I've run out of my time, so let me conclude. We have seen various examples which reinforce the picture that the landscape of consistent quantum gravities are finite. A refined version of the desert scenario may imply bounds on the number of masses mode as expected from finiteness. Compactness of the brain probe leads to the reconstruction of internal geometry in some cases. It would be nice to try to extend this to more cases and try to actually see whether or not we can actually explain why string landscape is related to consistency of quantum gravity from the infrared viewpoint using these ideas. And this provides further evidence for the string lamppost, at least in the examples with higher supersymmetry, as well as lending further support for the emergence proposal of the distance conjecture. Thank you very much.
Thank you. Are there questions? Miguel Montero. Miguel?
Sorry, I know I didn't have a question. I was just clapping.
Oh, sorry. Joaquin Taylor?
Yeah, thanks, Cumrun, for the nice talk. Very interesting stuff. I just had a quick question. In the last thing you were talking about, you said that you looked at 38,000 toric bases. So, you know, when Dave and I classified the toric bases for 6DF theory, we found 61,000. I'm just curious what your criterion was,
yes.
Like which subset you looked at and whether you think there's something wrong with the other part.
No, there's nothing wrong with the other cases. I mean, originally I had the whole base as part of it. The thing is that they had these blow-up modes you had to further do to get rid of these two cycles. So we didn't want to get to the complicated ones, so we had the simpler ones. But
very good. So you just didn't worry about the ones with that extra property.
Yes.
Cool. Thanks a lot. Very nice talk. Thank you.
Thank you.
Eva, you had a question?
Yes, I did. I didn't know I raised my hand. It's interesting to see these finiteness properties in the supersymmetric cases. But most compactifications are not supersymmetric, and most manifolds are not Glabiau. Most are negatively curved, and there we know that are infinite sequences of manifolds, and these manifolds are understood very, very well. There's nothing mysterious about them. So so in order to, establish some sort of finiteness conjecture, you would have to rule out compactifications on any hyperbolic space.
Yeah. So of course,
For example,
question: what happens?
among other things.
Oh, sorry, I thought the thing was finished. So yeah, indeed, Eva, as you say, we certainly do not have any claims about the general statement, which is much more difficult. Even the supersymmetric case is very hard to deal with. So and then the other ones, the non-supersymmetric cases, we have to deal with stabilization issues, which even with n equals to 1 supersymmetry is hard because of square potential. So here I was just focusing on the cases we have a much easier time. Clearly, even in this set, we should have no reason to have had finite. At least we should explain why if there's finite. And I want to focus on the case where we actually have strong evidence that's finite before we move on to cases which are harder to study. But yes, of course, we have to study more cases down the line.
Any other question?
Okay, thanks. I mean, one thing I would add is just that it's not always the case that the SUSY case is actually easier to study because it legislates against certain contributions that can help. And in product geometry, for example, we know the metric, whereas in Calabi-Yao's, we typically know the metric. We know the K3 metric now, thanks to Shamit and his collaborators. But say for hypersymmetric Calabi-Yao's, we don't. So in that sense, they're actually harder.
Yeah, the stability issue is the main thing that I think is the driving the discussion we had. Of course, if we had ways to understand stabilities, then that would be a different story.
Okay, I think we can stop here. Thank you again, Cumrun.
Thank you.
And there is a break now, right? I don't know if you want to say something. Organize this.
No, okay. So we'll be back, I guess, at 11. I don't have a schedule.
11:20.
11:20. Thanks. So Alex, do you want to try to share your screen?
Yeah, I'll give it a try here.
So you logged on twice, right?
Yeah, once with my tablet, which is the one that needs screen
Okay,
sharing.
fine. Okay, now they're both co-hosts.
Okay, thank you.
Okay, looks good.
Good.
Yeah. So you can stop the share screen. Try to find the others. So Thomas, do you want to try your share screen now?
Yes. It's okay.
Yep, looks good.
Okay.
Thanks. And Gary, you want to try?
Sure. Let's see. Do you see it in full screen mode?
Yep, looks good.
Okay. No strange color panel. Sometimes it comes with keynote, but
It looks good.
okay. All right. I think we're good. Let me stop sharing.
Mirjam will have her own share screen, is that right?
Yes. So
I'll find
she has her own slides.
Okay.
Let's see if I can. There we go.
Okay. Hi, Mark. I'll make you co-host.
Okay, thanks. I'm gonna go grab a coffee if
Sure.
we have a few minutes, I guess.
Mirjam. You want to just quickly check your share screen, Mirjam?
Yes, okay.
Okay, go ahead.
Okay, so I'll do it. Let me just see where my here. So you see it?
Yeah, we can see it. I don't know if you want to
into the mode of, yeah. Okay.
Very good. Okay, thanks, Mirjam.
Great, yeah. All right. So it's gonna continue directly after the talks, right? So, yeah. Okay, good. See you later. Bye.
Thanks, Mirjam. Bye-bye. You can stop sharing screen.
Yeah, let me do that too, of course. Okay.
Okay, whenever you're ready, Mark, we can start.
Okay. So welcome to this session, and we're going to start out with Alex May from UBC, and he'll tell us about some quantum tasks and their relevance to holography.
Okay, great. Thanks, Mark. So I just want to start out by thanking the conference organizers for the invitation to speak today. It's great to have such a broad audience for this work. So what I'm going to speak about is ADS-CFT and what causally defined features in the bulk of ADS tell you about correlations in the dual CFT. Okay. So I'll start out by recalling a sort of classic setup in ADS-CFT, which involves choosing 4 points on the boundary of ADS. So the points here are C1, C2, R1, and R2. And the way I'm going to choose them is such that these points scatter in the bulk, but do not scatter in the boundary. And what I mean by they scatter is that there exists some point P in the bulk, which is in the future of C1 and C2, and the past of R1 and R2. So you can see that this point here has that property in the bulk, but that in the boundary, there's just no such point. Okay. So if you try and meet up, say between C1 and C2 like this, then you can get out to R2, but not to R1, or you could do this way and get out to R1, but not to R2. Okay. So this observation is a little bit puzzling in a way, because you might think that there's some physics associated with being able to meet up in the bulk like this. And it's puzzling how the boundary theory can reproduce the same physics without having that point. And this has been thought about productively by a number of authors, famously by these authors at HPPS, who understood that for the boundary to reproduce the bulk physics associated with this point, the boundary theory needs to be large n and it needs to have a gap in its spectrum. Okay. So in this talk, I'm going to be thinking about sort of similar or analogous setups where there's some causally defined feature in the bulk that's lacking in the boundary. And what we'll think about is how do these bulk causal features constrain the state in the boundary as opposed to the boundary theory. Okay, so how does it constrain the state? And what we'll see is that these bulk causal features have implications for boundary correlations. Okay, good. Okay, so that's sort of the question for today, and here's how I'll go about addressing it in this talk. So I'm first of all going to recall some ways that you can measure correlations just in quantum states in general. And then since we're in a holographic context, those measures of correlation will have some interpretation in the bulk in terms of extremal surfaces coming from the Ryō-Takanaki formula. And then in the second and third parts of the talk, I'll state 2 theorems that begin addressing this question. So I'll state what's called the privacy duality theorem, and then also the connected wedge theorem. And what each of these does is relate some causally defined feature in the bulk to a different measure of correlation in the boundary. Okay. And as I go along, I'll try and explain how to understand why these theorems are true and where they come from. And that will lead us to think about quantum information and how it can move through and evolve in a space-time context. So I'll try and highlight that as I go and make more clear what I mean by that once we get into it. Okay, and then at the end, I'll wrap up with a few comments. Okay, so let me jump in talking about how to measure correlations. So there's going to be two objects that we're concerned with. The first is the mutual information. It's a measure of how correlated two subsystems of a quantum state are. So we're going to call those subsystems A and B. And the way it's defined is as the von Neumann entropy of subsystem A plus the entropy of system B, and then minus the entropy of their union. Okay. The second object that we'll care about is called the conditional mutual information, and it's defined as this difference of mutual informations. And the way that you should think about this is as the amount of correlation between system A with the union of BC that wasn't already present between just A and B, right? That's why we're subtracting off this second term. Okay, good. So those objects, those ways to measure correlation are built out of this von Neumann entropy. And we know that in holography, there's a simple way to calculate the von Neumann entropy using bulk degrees of freedom. So if I have some boundary subregion, which I'll take to be this region in orange here, V, the Ryutakanaki formula tells me that to calculate the entropy, what I do is look at the area of some extremal surface that sort of encloses V like this, divide that by 4G Newton, and then add to that the entropy of the bulk fields in this gray region in here, where the gray region is the thing bounded by the extremal surface and V. Okay. So another thing to tell you about here is that if I give you the density matrix on the subregion V, what's been understood is that this records all of the bulk data inside what's called the entanglement wedge of V that I'll denote E sub V. And I've drawn here. And the way that this entanglement wedge is defined is just as the domain of dependence of this gray region up top. Okay. And then this fact that this density matrix records all the bulk data in this wedge, I'll refer to as entanglement wedge reconstruction, and I'll use it a few times in the talk. Okay. So the last sort of background thing to tell you about these measures of correlation is that the order of these correlation measures records qualitative features of extremal surfaces, right? So they're expressed in terms of the von Neumann entropy, and then the entropy is expressed in terms of the areas of extremal surfaces. And consequently, we learn things like if, say, the mutual information is order 1, that it implies that the extremal surface enclosing the union of A and B sits this way. And if it's order 1 over G Newton, then the extremal surface sits like this. Okay. Another way to say this is that in this case, the entanglement wedge is 2 disconnected regions, and in this case, it's 1 connected region. Okay. Good. Okay, so that's sort of the background and how I'm going to discuss correlation. Now I can state the first of these 2 theorems. So the first one's called the privacy duality theorem. And the way it works, at least roughly, is the following. So what we're going to do is pick a wedge down here. So this is the entanglement wedge of some boundary region, C. And then we'll pick another wedge somewhere up here, which is the wedge of some boundary region R. Okay. And then what we do is we check if there's a causal curve from the wedge of C to the wedge of R that avoids the wedge of some third region that I'm calling U. Okay. When a curve has that property, that it avoids the wedge of U, I'm going to call it a private curve. Okay. And then what the theorem says is that if there's such a causal curve, then the conditional mutual information between V1 and V2 conditioned on U is order 1 over G Newton. Okay. I haven't specified yet how I'm defining the regions V1 and V2, but you can get a sense of what they are from the picture. V1 is this, or is the domain of dependence of this blue region here, and then V2 is the domain of dependence of this blue region over here. Okay. So let me be a little more precise and tell you how V1 and V2 are defined. So to define it, start with the region U, and then draw a Cauchy surface that goes through the region U. So maybe something like this. We'll call that sigma. And then what I'll do is take the intersection of sigma with the space-like complement of U. Okay, and so that picks out, say, this interval plus this interval over here. Oh. And then looking at that interval, what I do is I look at the future of C, and I call the portion that's in the future of C, V1. And then the portion that's in the past of R, I call V2. Or more properly, I call the domain of dependence of these intervals V2 and this domain of dependence V1. Okay, so that's precisely what I mean by V1 and V2. So now let me just say the theorem one more time now that you know what that is. So we're saying if there's a causal curve from down here to up here, then this V1 region and this V2 region are correlated in this precise sense. Okay. So we can see that this theorem is starting to address this question I started out with, in that it's relating some causally defined feature in the bulk, namely the existence of this causal curve, to a property of correlation in the boundary, specifically this conditional mutual information being large. Okay. Okay, so to understand this, and actually to understand various kinds of theorems that have this property that relate causal features and correlation, I claim you can use the following general sort of procedure. Okay, so the procedure goes in 3 steps, and the way it works is in the first step, you introduce some sort of probe quantum system that we're going to call Q, or in some cases we'll have systems QI. We introduce those to the bulk and then exploit the fact that this causal feature exists to have Q evolve in some interesting way. Okay, so we're going to have something interesting happen to Q by virtue of this causal feature existing. Okay, and then the second step is I want to translate that evolution of the system Q to some evolution in the boundary. So I want to think about how does the quantum information stored on Q evolve in the boundary picture. Okay, and then in the third step, we think about that evolution in the boundary picture and note that in the boundary, we'll be lacking this same causal feature. And from that, we'll be able to argue sort of at the level of quantum information that appropriate correlations are necessary for the boundary to reproduce that evolution. Okay, good. So let me, so that was sort of the general picture. It's a bit high level and maybe sounds a bit vague. So let me go through those steps concretely in the context of this privacy duality theorem. Okay, so the first step is we introduce this probe system. We'll just need one here, we'll call it Q. We're gonna think about the state stored in the system Q, and I'm gonna call it psi. And then what I'm going to do with Q is record it into the bulk somewhere and send it along this causal curve gamma. Okay, so Q starts down here in the wedge of C. It travels through the bulk and ends up here in the wedge of R. Okay. And how I'm going to think about this is this sends the message, some message, which is the state psi, from the wedge of C to the wedge of R, and specifically it sends the message in a way that keeps it secret from the wedge of U, right? That was a property of this curve gamma, that it stays out of this region. And so we see that this message is sort of secret in a certain sense. Okay, right, and then the second step was we wanted to understand what does this mean in the boundary picture. Okay. And we can use this entanglement wedge reconstruction fact to understand that. So what we learn is that, first of all, since Q starts out in the wedge of C, the state psi is initially available in this boundary region C. And then later, since Q ends up in the wedge of R, the state psi is available up here in the region R. And because Q stays out of the wedge of U, we know that in between, psi is never available in the region U. Okay. So another way to say this is that the density matrix on U is independent of the choice of state psi. Okay. So the boundary picture here is a little bit puzzling because, again, we're lacking this sort of causal feature. In particular, all the causal curves from C to R are not private, so they all go through the region U. Okay. And so the puzzle is sort of how can we start with the information, or start with the information here in C, end up with it up here in R, but never have it pass through the intermediate region, right? And the resolution to this puzzle, you probably won't be too surprised to hear, is that the boundary exploits correlations among its subsystems to sort of hide the state on psi as it passes through the region U. Okay. And this is what in the end will lead to this requirement that this conditional mutual information is large. That's exactly the sort of correlation it needs to send this secret message. Okay. So I won't have the time to give you that argument in detail, but what I will do is try and at least give you a sense of how correlations among subsystems can be used to hide quantum states or quantum information. And the simplest way I know how to do this is using what's called the quantum one-time pad. Okay. So the way the one-time pad works is you prepare a string of random bits, which I'll call K. So maybe this is like 0, 1, ... And then we make a copy of K. So this is the same string, 0, 1, ... And what I'll do is I'll bring this copy of the string over here, which I'm going to think of like the region C. And I'll use K to pick a unitary, which I'm going to call P sub K, and apply it to the state psi. Okay, so I'm going to have some big set of unitaries I could draw from, and then which one I pick will be based on the value of K. This is going to sort of encode the state for me and hide the information, but it produces this state pk psi, and I take that and I just send it through the region U. Okay. Meanwhile, this string over here, I take through region V2 and up to what I'll think of as near the region R, and use my knowledge of K to do pk inverse and produce the state psi, right? And an important fact about what's happened here is that the string K never enters this region U. Okay, so from the perspective of calculating the density matrix on the subregion U, K is just unknown, and I should average over it. And what happens is if you choose this set of unitaries correctly, and then when you average over them, you'll just get the identity, which in particular is independent of your choice of state psi. Okay, so this, you can see, accomplishes what we wanted in that we start with the state down here in C, end up with the state up here in R, but in between it just looks like noise. Okay. Importantly though, the string K passes through region V2 here, and over on this end, just because of unitarity, and I brought K here, K has to go somewhere, and I don't want it to go in U, so it has to come up here into region V1. Okay, so as a byproduct of sending this secret message, we've ended up with K stored in V1 and V2, and so in particular, V1 and V2 are correlated. Okay, and yeah, so that's how we can see that correlations between subsystems help you send these secret messages. Now, what I've shown here isn't the most general thing you could do, okay? This is just one particular thing. But what you can show is that anytime you succeed in sending this secret message, this quantity, the conditional mutual information, is large. Okay, and then that's what leads to the conclusion of this theorem. So to sort of summarize the reasoning, it's basically this private curve in the bulk lets you send a hidden secret message. There's no private curve in the boundary. So to reproduce that evolution, the boundary instead replaces the private curve with a large amount of correlation of this particular type. Okay, good. So that's the first theorem. Now let me give you the second example of this, which is called the connected wedge theorem.
Just chiming you about 5 minutes.
Okay, thanks. Okay, so the connected wedge theorem, I'll be briefer. The way it works is you pick 4 wedges, okay? So we have the wedge of C1, the wedge of C2, and then the wedge of R1 and the wedge of R2. And then what you do is you check if these wedges scatter in the bulk in some sense, okay? So in particular, you're gonna check if this region, which I'll call the scattering region, is non-empty, where the scattering region is defined by looking at the future of the wedge of C1, the future of the wedge of C2, the past of the wedge of R1, and the past of the wedge of R2, and intersecting all of those. So for instance, this point here is in the scattering region. And then what the theorem says is if this scattering region is non-empty, then the mutual information between 2 associated boundary regions, V1 and V2, is order 1 over G Newton. Okay. V1 and V2 are defined by looking at, so for V1, we look at the future of C1, okay, and then the past of R1 and the past of R2, and that defines this larger diamond here. And then similarly for V2, but you use the future of C2, okay, and you get this diamond over here. So again, we're seeing that some causally defined feature in the bulk, namely whether this scattering region is empty or not empty, is telling you about correlations in the boundary, specifically this mutual information. Okay. Another way to think about this, given what I said earlier, is that this large mutual information is associated to the extremal surfaces sitting this way. Okay, so I won't give a detailed argument, but what's important is that this theorem also follows from the same strategy that I outlined before for the privacy duality theorem. The way that it goes roughly is you introduce 2 probe systems, which are going to be Q1 and Q2, and you make use of the fact that this scattering region exists to do some local unitary on Q1 and Q2. So you can bring them together because the region exists. You do some local unitary, and then what you argue is that in the boundary, for the boundary to reproduce that local unitary, it needs this large mutual information. Okay, so it's the same sort of idea where we're thinking about the dynamics of quantum information. Okay, so that's all the content I wanted to say. I'll just wrap up with a couple of comments. The first comment is that, in general, in ADS-CFT, we have this very interesting connection between geometry in the bulk and entanglement in the boundary. And I think, so that connection, as we usually understand it, comes from the Ryutaganaki formula, and it relates bulk extremal surfaces specifically to boundary correlation or entanglement. And what I think these 2 theorems taken together suggest is that there's another sort of connection between geometry and entanglement, which is between bulk causal features and boundary correlation. Okay, and instead of being given by the Ryutaganaki formula, the connection is given by thinking about quantum information as it moves in space-time in the way that I've tried to outline. Okay, so this sort of fleshes out the entanglement geometry connection in an interesting way. And I think by fleshing it out like this, you get various things. So one really simple thing that you get is you can just follow these implications through like this, right? relate causal features to correlation to extremal surfaces, and end up with a connection just between causal features and extremal surfaces at the end. And so this ends up being just a purely geometric statement, right? Between two bulk geometric objects. So you end up with just some interesting statement about ADS spacetimes. And actually in both the cases that I showed here, you can just use direct GR proofs to reach the same conclusion. Okay. Another thing that you get here is, we get this different geometric way of thinking about entanglement. And so you can kind of revisit problems that we previously studied using extremal surfaces and ask if this causal perspective offers something new. And concretely there, what I have in mind is in the context of black holes and island formation, usually we study extremal surfaces to see when the island forms. Here you can look for maybe a causal condition for an island to form. And indeed, at least in some toy models, my collaborator David Wakeham and I were able to find such a condition. So I think that's also an interesting direction moving forward. Okay, so that's everything. Thank you, and I can take questions.
Okay, let's thank Alex. So we have some questions. The first one I saw was from Pedro.
Yeah, can I just ask a quick question? Maybe it's naive, but I was confused that the dimension was not playing a role in the discussion. And as Sasha Zhiboyedov also pointed out in the chat, I was used to these pictures where, say, to localize a point in 5D, you need like 6 points in the boundary from this work of Sasha, Juan, and David. But here, dimension was not showing up at all. Could you comment a little bit on what I'm missing?
Yeah, so that's a great question. It's a little bit complicated. So the theorems, as I've stated them, are true in any dimension. But for say, okay, so let's say think about the connected wedge theorem, right? So I was drawing this kind of picture, and there's wedges, but we can just think about it as points for now. And there's something like this. And so what's important here is that there's a scattering region in the bulk, but not in the boundary. And what happens in, say, like global ADS in one higher dimension is that if you just have 2 input points and 2 output points, then whenever there's a scattering region in the bulk, there's also a scattering region in the boundary. When that happens, V1 and V2 will just overlap. And so the mutual information between them, you could think of it as infinite, or you could think of it as ill-defined. But yeah, so the theorem sort of becomes trivial when you don't have this fact that like the scattering region in the bulk is non-empty and empty in the boundary. So the theorem is true, but trivial in global ADS in one higher dimension. On the other hand, if you don't use global ADS, like say you use the ADS soliton, so the boundary is a spatial cylinder, then there's non-trivial configurations and the theorem applies in an interesting way. So yeah, I think with the connected wedge theorem, it's like a remaining challenge in the future to understand better, say, situations where we have 2 to 3 scattering, and then that would remain non-trivial in higher dimensional global ADS. For the other theorem, the privacy duality theorem, you can always find non-trivial configurations even in higher dimensions, basically because you have this flexibility of choosing the region U in a lot of different ways. It's sort of this extended region, and you can play with it to get what you need.
Okay, let's go to Hiroshi, I think was next.
Yes, so I thought that to derive these theorems from boundary perspective, you may need some information like large N or existence of gap. And I'm not sure where or whether they appear in your one-time pad argument, which I believe is about on the boundary. Could you explain?
Right. So actually sort of an interesting thing about the way this reasoning works is you don't really need to know very much about the boundary. All I use about the boundary is that it's quantum mechanical, so it's unitary and relativistic, so it has these light cones. But yeah, the way the theorems
so
work.
you don't need a weakly coupled bulk dual.
Well, yeah. So you use the existence of the bulk. So we say for this theorem, we say, okay, this scattering region in the bulk exists. We're going to assume some unitary can happen in the bulk, and then that says something about what happens in the boundary. And then what you assume about the boundary is just that it's unitary and relativistic, and then the argument goes through.
So is this like some kind of a toy or caricature of what's happening in the bulk? Is it really a boundary proof?
Okay, I shouldn't call the boundary proof a proof. There's a little bit of a loophole. You can prove it. Okay, so for this theorem, you can, in general relativity, prove that if the scattering region exists, then it implies the extremal surfaces sit this way. So this is a proof from the focusing theorem, right? This is just the geometric sort of argument. The quantum mechanical proof has a little bit of a hole in it. I believe it, but okay, there's a bit of a problem. And the way it works is just doing what I said. So you're just saying, from the bulk picture, that a certain evolution happens, certain information ends up at certain places. And then at the level of quantum information, you can argue that this entanglement is necessary. And you don't use that you're large N or gapped or anything like this, just that you're unitary and relativistic.
Okay, thank you.
Yeah.
Okay, so yeah, unfortunately, we should move on. So I'll invite the others with questions, perhaps to put the questions in the chat. So we should move on to Thomas Mertens.
Thanks.
So maybe, yeah, let's thank Alex again one more time before. Very nice talk. So Thomas, you can share. Okay, and so we're happy to have Thomas Mertens from Ghent University, who will tell us about Liouville and JT quantum gravity, holography, and matrix models.
Okay, so let me first thank the organizers for inviting me to give this talk. So I'm going to talk about Liouville and JT quantum gravity, and I'm going to try to phrase Liouville gravity from the perspective of holography and matrix models. And my talk will be roughly based on these two papers that have appeared last year. So let me start by giving you an introduction. So there have been many developments in the last couple of years in lower dimensional gravity, and in particular in JT dilaton gravity. For example, we have learned how to think about higher genus and multi-boundary amplitudes, and these turned out to be important to understand the very late time behavior of correlation functions. We have learned about these replica wormholes, which are important to understand the page curve, and so on. We have also learned about an exact quantum solution of these boundary correlators and their interpretation in terms of gravitational physics explored in these papers. And there have been many more developments in this model. So I just write down a couple of these. So for instance, wormhole traversability, finite cutoff versions of this model, explicit island calculations, bulk reconstruction, and so on. So we have learned a great deal about how quantum gravity behaves for this particular model for JT gravity. So it would be interesting to extend our class of solvable models to find out how generic these lessons are. And the goal of this talk is precisely to discuss a single such model, 2D Liouville gravity, or the minimal string, and to try to phrase it in the same language as we have been learning about JT gravity. So let me start by giving you a brief review on JT gravity. So I've written down the gravitational action here. And of course, I've added a negative cosmological constant because I will be interested in ADS2 spaces and I will do holography. So what is interesting about this gravity model is that you can compute a lot of the amplitudes completely exactly. So I will just sketch or just give you some of the answers of these calculations. So the simplest one is the disk partition function, first calculated in these papers 5 years ago. So this is the case where we have a single holographic boundary, the circle here of circumference beta, which will be the inverse temperature, and we path integrate over all of the gravity fluctuations in the interior. Now there's an exact answer for this, which I have written here. So you can write it as an integral over k where k goes from 0 to infinity. There's this measure k times sinh 2 pi k, and then the Boltzmann factor e to the minus beta k squared. So this is obviously a canonical partition function where the energy variable E is just k squared. Now it is interesting to do a thermodynamic limit of this exact answer. So this means just evaluating this integral at its saddle. So in this case, the density of states, which is sinh 2 pi square root E, just becomes an exponential. And you solve for the saddle equation and you find square root E is proportional to the temperature. And this is an interesting relation because this matches precisely with the black hole first law. So mass versus Hawking temperature for a semi-classical JT black hole. But this answer generalizes it. This is the full exact canonical partition function. So the next object we will need during this talk is the boundary 2-point function of some boundary CFT matter operator OH of conformal weight H that is being coupled to gravity. And this has been calculated in these sets of papers during the past couple of years. So we take two of these operators at the boundary, one at time tau 1, one at Euclidean time tau 2, so at the boundary of this disk, and then we do the gravitational path integral. And the answer is known exactly, and it's given by this long expression. So this expression contains two integrals over this momentum variable k, k1 and k2. We have the same measure that we had in the partition function twice. We have these Boltzmann suppression factors or Hamiltonian propagation factors. One of them has this time tau, which is tau 2 minus tau 1. So it's just the time difference between the two operators. And then the other one has the complement on the thermal circle. And then there's this bunch of gamma functions. And whenever I will write this plus minus symbol, I will mean that you have to take the product of all cases. So there's secretly the product of 4 gamma functions in the numerator. And this is the object that couples these two integrals together. So we will later on see the same structure appear for Liouville gravity as well. And the last thing that I will need from JT gravity is the exact answer for the multi-boundary amplitudes, which was beautifully explained in this paper by Sachenker and Stanford. So what I've drawn here is an example of a multi-boundary amplitude where I have n boundaries of boundary length beta 1, beta 2 up to beta n, and they're connected in the interior through some complicated higher topological object here. And there's an exact answer for this amplitude in JT gravity, which I have written down here. So let me go through the different ingredients. So first of all, you see this ZJT beta I bi. This is a single trumpet partition function. It only depends on one of these asymptotic betas and one of these interior B parameters, and it has a very simple expression, which I've written down here. You can think of these as JT disk partition functions with a hyperbolic defect B. Now these B parameters, so I have B1 up to Bn, these represent the geodesic lengths of these necks as you glue these exterior trumpets to this interior object here, and we will integrate over all of these n geodesic length parameters. And we will do that with a specific measure, which is dB times B. Now this factor of B arises because when we glue these tubes together, we can do that with a twist. So we can twist the two tubes before gluing, and that twist parameter can range between 0 and B, and that explains this additional factor of B we have here. And then finally, we have this interior object, VGN of B, which only depends on all of the B parameters, on all of the geodesic lengths. And this is the Weil-Peterson volume. This computes the volume of the moduli space of Riemann surfaces of genus G with n geodesic boundaries of lengths B1 up to Bn. And these are multivariate polynomials in all of the B squared, and they are known through recursive relations by Mirzakhani's work. Okay, so I want to phrase Liouville gravity within this same language. I want to see a generalization of this structure appear in Liouville gravity. So let me first of all define what I mean by Liouville gravity. So I will mean the non-critical string you get by coupling conformal matters to 2D gravity, or alternatively the critical string with 2D Liouville matter and ghost CFT coupled together such that the total central charge is 0. The action of this model is just the sum of the Liouville matter and ghost pieces. So let me be a bit more explicit. So the first piece is the Liouville action, which I've written down explicitly here, is the standard action for the Liouville field phi. It's parameterized by this quantity big Q here, where big Q is B plus 1 over B, and B is the parameter you use to define Liouville theory. It appears here in this exponential potential. And Liouville theory has a central charge, which is 1 plus 6Q squared, which will be bigger than 25. You can think of this field phi or this Liouville field as arising from the conformal factor from the non-critical string, because I can write any 2D metric as just a conformal factor times some reference metric, and all of the dynamics is contained in this conformal factor, which is governed by this Liouville action. Secondly, we have the matter piece in our theory, and for most of this talk, this matter piece will be just an arbitrary CFT with central charge less than 1. But for some cases, and well, I will mention that later on, we can specify to the Q, P minimal model where Q and P are integers. And this will, well, this is called the minimal string. And the reason that I will specify to that later on is because this minimal string has a matrix model description, which we can exploit. And then finally, of course, we have the ghost action, which is the usual BC ghost theory with central charge minus 26. Now, I will be interested in studying this model on fixed length boundaries, or with fixed length boundaries, because I will reinterpret these world sheet amplitudes as quantum gravity amplitudes. And because I'm interested in holography, I will need, or these world sheets will need to have a boundary of fixed physical length beta, where beta is the inverse temperature, because I want to be studying thermal amplitude. So this is just like the discussion I gave on JT gravity in the beginning. So we will need to think about boundary conditions. So for the Liouville piece, the boundary conditions that we will use are FCCT brane boundaries introduced by Fateev, Zamolodchikov, and Teschner. And you can get those by adding a boundary action to the Liouville action like this, which is parameterized by this real number mu b, which is the boundary cosmological constant. Now, when viewing the theory as 2D quantum gravity, as I mentioned, the Liouville field is related to the metric by just this conformal prefactor, which means that the boundary length, if you compute it using this Liouville metric, is just the line integral of e to the b phi. Now, this gives you a strategy to compute the fixed length amplitudes, because in the path integral, you can just do this Fourier transform over mu b, where mu b goes along the imaginary axis. You multiply by e to the mu b L, and because mu b only appears linearly in the action here, once you do this Fourier transform, you just extract this delta function, where this boundary length is fixed to this number L, which will be, of course, then the boundary length. And this generates a delta function on this boundary length. Now, there is a generalization of this that I will also need, which is, well, I can consider a boundary with piecewise constant values of mu b. And then I do multiple of these Fourier transforms, and that will allow me to get to a boundary with fixed length segments L1 up to Ln. I will also be interested in adding operator insertions. So I will consider the amplitude with insertions of specific bulk and boundary tachyon vertex operators in this model. So this is the general calculation that I want to be doing. So I have a couple of boundary operators, B1, B2, and so on, separated by fixed length segments on the boundary, and then a couple of bulk tachyon vertex operators in there. Just to be very specific, let me write down a couple of expressions. So these are just the standard vertex operators you use in string theory. So the bulk tachyon vertex operator, for instance, is a CFT operator from the matter sector, which is dressed by the Liouville piece, such that the sum of their conformal weights is 1, and then you integrate it over the world sheet, or you can write it in this gauge fixed way as usual. And then you have a very similar expression for the boundary tachyon vertex operator. You take a matter operator, dress it with Liouville, and well, with the same constraint. So these are just the standard kinds of operators. So this is the thing that I want to be thinking about and that I want to start computing. So let's start with the simplest case, which is just the disk amplitude, the one where there are no additional vertex operator insertions. So we look at the literature, and we look at the known disk amplitude with an FCCT brane boundary, which is written down in these older papers. So this is at fixed mu b, and this is what you find in the literature. So it's cosh 2 pi s over b, where this s parameter is related to the mu b, the boundary cosmological constant, and by this formula. There's a prefactor kappa here, which I write here, but I will set it to 1 just to streamline the formulas during this presentation. And now we just need to transform this object to the fixed length basis. So just apply this Fourier transform. And without going through the details, this is the answer you get. So this is what I believe a very suggestive answer. So you can write it as an integral over this s parameter from 0 to infinity. There's a measure, which is sinh times sinh, as you can see here. And then there's this exponential factor e to the minus length of the boundary cosh 2 pi bs. So this formula is very suggestive. And in particular, it has a nice limit where it goes back to the JT answer that I showed you at the very beginning of this talk, which is you can take this double scaling limit where b is going to 0 and simultaneously you let the length go to infinity in this particular double-scaled way. If you plug that in here, you immediately find that this disk amplitude reduces to the disk partition function for JT gravity. So now let's go back to the full Liouville gravity result. As I mentioned, I want to interpret the boundary as a thermal holographic boundary, and in particular, this length parameter L, I want to think about this as the inverse temperature. So it's a very easy step to rewrite this literally as a canonical partition function from which you can read off the density of states, which is sinh of an arcosh of the energy, basically. And now it's interesting to think a bit about the thermodynamic limit of this, because that is where you would find black holes in the bulk of this model. So you just do the saddle approximation, and you find this first law that I've written here. So square root E squared minus 1 is proportional to the temperature. Now, there are two regimes that are interesting. In the IR, where the energy is small compared to this cutoff that I called 1 here, you'll find back exactly the JT black hole first law. But in the UV, you find that the energy is proportional to temperature. So this model reduces to JT gravity in the IR, but modifies it in the UV. Now, if you think about this model in holography, where you have this UV-IR connection, this would mean that there's a qualitative change of the boundary region of the bulk geometry. So this Liouville gravity model will not be asymptotically ADS like JT gravity is. Okay, so that was everything I wanted to say about the disk partition function. Now let's add a complication and go to the bulk 1-point function. So I take the disk amplitude and I insert one of these bulk tachyon vertex operators. And again, I want to transform the known amplitude with the boundary FCZT brane to the fixed length basis. So there's a simple calculation that you can do, which I'm going to omit again. And this is the answer you find. So again, this has a structure that is very similar to the previous example, to the disk partition function. And you can do this integral explicitly, and I write it here. So you can do it in terms of a modified Bessel function k here, where the index has this label p, this big P, and this big P is related to alpha in this typical Liouville way. And alpha was the parameter that I used to characterize my bulk operator insertion here. And then the argument of this Bessel k function is the boundary length. The reason that I'm so explicit about this formula is that it will reappear in the next couple of slides. So using this bulk 1-point function, we can study, as a tool, we can study these multi-boundary amplitudes and try to phrase them in the same language as we did those of JT gravity. So to study multi-boundary amplitudes, we will start with the simplest case, which is the Euclidean wormhole, or just the annulus amplitude. So 2 boundaries. And the calculation has been done in Liouville gravity by Martinek almost 20 years ago. So the calculation that I'm imagining here is you have 2 of these boundaries, you compute the annulus amplitude, and this is just a standard calculation in string theory. So you have a worldsheet modulus tau, which is the length of this cylinder, and then you take the product of the 3 cylinder partition functions for Liouville, matter, and ghost between suitable boundary states. Now this is for fixed boundary states, but again, you need to transform this to the fixed length boundaries in order to make contact with our goal. And this is explicitly calculable for several choices of the matter sector. But now I'm going to specify to a specific matter sector. The matter will be the 2, p minimal model. So the entire theory will be the minimal string. And the reason I will do that is because this has a 1 matrix model description that I will exploit on the next slide. So with this specification for my matter sector, this is the answer you find for the 2 boundary amplitude. And this is a very suggestive way of writing it, because you write it as an integral over some parameter lambda, some gluing measure lambda tangent by lambda, and then a product of 2 of these Bessel k functions, where the index is precisely the parameter that we're integrating over, and the arguments are the 2 boundary lengths L1 and L2. So you can read this as 2 bulk 1-point functions. So remember from the last slide, the bulk 1-point function was precisely this modified Bessel function here. So this is readable as 2 bulk 1-point functions, where the lambda and the p parameter characterizing the bulk operator insertion are related like this, that are being glued together by integrating over lambda. So this is the geometrical picture that this calculation is associated to. So this was just for 2 boundary loops. Now we can go to multiple loops, to n boundary loops, by using the fact that our entire theory is given by a matrix model. So at genus 0 for n boundary loops, there is this very elegant formula from Mohr-Seiberg and Staudacher from the early 90s, where if you know just this function u of x and you insert it in here, you just need to compute some derivatives and set u equal to 1 in the end, you will compute the genus 0 answer of this. Now, what is u of x? Well, u of x can be determined as soon as you know rho 0 of E, so the disk density of states. And we computed that explicitly, or we wrote that down explicitly for this model. This was the sinh of Arcosh function. So given knowledge of rho 0 of E, you can, well, find this function f of u from this equality. And knowing f of u, you can find u of x immediately. You plug it in the first equation, and then you find the answer. So we give some formulas for that in our paper. But here I want to focus on seeing whether the structure of JT gravity is present in this calculation as well. So what I've done on this slide, I've rewritten this exact answer as an n-fold integral over auxiliary parameters lambda 1 up to lambda n, each with this gluing measure, lambda tangent pi lambda, that we had for the two-loop amplitude on the previous slide, these Bessel K functions that we also had on the previous slide, and then an object that just depends on these gluing parameters lambda 1 up to lambda n. And I will view this as the definition of this object, phi0 n of lambda. Now, this is a sensible definition since this integral is an invertible integral transform. So it uniquely defines this object. And you can think of this as a rewriting in terms of glued bulk one-point functions. So these are these Bessel Ks, where this V0 n of lambda is some sort of deformed genus 0 while Peterson volume. And you can find an explicit formula for it just by literally inverting this, these equations in terms of the Legendre functions, which I write here. So all of this was just for genus 0. Higher genus corrections can be obtained through matrix model techniques, through topological recursion formulas from Hénard and Orantin. And using those, we can give a generic proof that VGN, so at genus G, of lambda is a multivariate polynomial in lambda I squared. So this is in parallel to the statement of the ordinary Weil-Peterson volumes. So to summarize this discussion, at genus G, the n boundary loop amplitude can be decomposed in this way, where you do an n-fold gluing integral with this gluing measure. You have this object that only depends on these gluing parameters that you can think about as being in the middle somewhere. And then you have n of these bulk one-point functions that you glue to these n. So this is in parallel to the single trumpet piece that you add in JT gravity.
You have about 5 minutes.
Okay, thanks. And well, I wouldn't be telling you all of that if there wasn't a nice JT limit, which you can take. And indeed, you get back the entire Schenker-Sanford procedure in ordinary JT gravity or hyperbolic geometry. And in particular, this gluing measure, it turns out that you need to scale lambda in this way. So lambda is going to infinity as you go back to JT gravity, and then the tangent is going to 1, and you get precisely dB times B. So that was the gluing measure you would use in ordinary hyperbolic geometry. So you can think of this morally as some sort of Q-deformed version of hyperbolic geometry. Now, the last object that I want to be studying is the boundary two-point function. So I add two of these boundary operators, so operators of this kind, and I have fixed length boundary segments in between of lengths L1 and L2. We again look at the known boundary two-point function in the Liouville theory for fixed boundary FCCT branes, so where there are two mu b parameters, mu b1 and mu b2. They're both related to S1 and S2 by a formula like that. Then the Liouville boundary two-point function that you find in the literature looks like this, where this SB is a double signed function. So there's a product of 4 of these double signed functions in the denominator here. Again, you transform this thing to the fixed length basis, but now for the two boundary cosmological constants, you find this object here. So it's a double integral over S1 and S2. It has two insertions of densities, which are sinh times sinh, e to minus cos 2 pi b S1 L1, and the same thing for L2. And then these SB functions here that couple the two integrals together. So there are 4 of these SB functions in the numerator. So the structure is very reminiscent to the boundary two-point function you would write down in JT gravity, if you remember it from the beginning. And indeed, you can just take a JT limit of this. So you take again b to 0 and some suitable scaling of the other parameters, and you literally find the JT boundary 2-point function from this. Now, the last thing that I want to mention is that, well, I've already alluded to this, is that these these Liouville gravity amplitudes, they have a quantum group interpretation, which is in parallel to the way ordinary JT gravity has an ordinary group theory interpretation. So it is known that the ingredients in JT gravity amplitudes have an interpretation in terms of the SL2R BF theory. So the objects are given in terms of group theory. Objects like the Planck-Schrödinger measure, Casimir 3J and 6J symbols of SL2R, or at least some modification of SL2R. And quite similarly, Liouville gravity amplitudes arise from the Q-deformed SL2R group, where the deformation parameter is e to the pi IB squared, as usual, where B is this Liouville parameter. And to show that, I want to mention that there exists a continuous set of representations for this quantum group that are self-dual. So they were first studied by Ponceau and Teschner in the late 90s. And these representations, they have the following properties. So the Casimir operator for these representations is characterized by a number S and is given by cosh to pi bs. This was precisely the thing that appeared in these exponential factors that we had. So this is the energy variable. The Planck-Schrödinger measure on these sets of representations is sinh times sinh. This precisely matches with our density of states. And then finally, you can compute 3J symbols of suitable representations of this Q-deformed group. And I'm going to skip the details here. And these 3J symbols match precisely with this object here. So this product of double sign functions. So this entire amplitude has a group theoretic interpretation, but in this case, it's a quantum group, whereas for ordinary JT gravity, it's an ordinary group. Okay, so let me conclude. So I have investigated fixed length amplitudes of Liouville gravity, and I try to phrase these in the same language as we think about JT gravity. And there is also a JT limit of all of our amplitudes where you take the Liouville parameter B to go to 0. In particular, the old string worldsheet genus expansion of this model gets reinterpreted in terms of a multi-universe or a space-time expansion. There are several things that I would like to understand better. So the n equals 1 supersymmetric generalization has been worked out to some extent, but there are still some things to think about. And then another point, I didn't have time to mention this, but there is a dilaton gravity interpretation of this entire Liouville gravity model in terms of a model with a dilaton potential that is hyperbolic sine function. So that is definitely something that I think, I definitely want to think about this in the future. And finally, it would be interesting to also think about more general dilaton gravity models. For instance, there's been this work related to deformations of JT gravity, and also the fact that any dilaton gravity can be written as a Poisson sigma model is also very suggestive and studied in several works. Okay, so thank you very much.
Okay, so let's thank Thomas. And we have time for some questions. Yeah, go ahead, Shoda.
Okay, thanks for the talk. I just had a small question. So is there a quantum analog of the Schwarzschild and like a co-adjoint orbit?
I'm not aware of that. There is a Q-deformed analog of the Virasoro algebra. So because you want to study co-adjoint orbits, of course, of the Virasoro group, if there is a Q-deformed version of the Virasoro algebra, one might be able to do that, but I'm not aware of any formulas that actually do it.
I see. Thanks.
Let's see. Any other questions? Okay. Well, if not, I guess we're on schedule. So I think I should pass it off to the next co-host. But let's thank Thomas again for a nice talk.
Thank you.
Okay, very good. So thanks a lot, Mark. And maybe I can then, since we are a little bit ahead of time, take this opportunity to make just a few announcements or comments, also because I see that there are so many new people in the chat today compared to the previous discussion. So I think it's good to just remind people how these discussions and so on work. So before, let me just make a small comment about Slack. So I'm very happy that many people are using Slack and writing lots of interesting questions, and also I think very useful after the conference, posting many useful references that we can all go back and check out later. So in that sense, please use Slack, and feel free to already use other sessions that are in the future. For example, for Thomas, it probably doesn't make much sense to use today's string phenomenology Swampland discussion to have questions about JT. Maybe you can put the questions on the average session discussion that we will have on Friday. So feel free to already spread out through these other sessions, not only making suggestions for things to discuss, but also asking more questions about the talks. And I hear Slack pinging, probably people are following my advice as I speak right now. So about this discussion. So let me remind what the idea is. The idea of this discussion is to have this more formal component of the conference so that we are all seeing each other. So do turn on your cameras when possible and engage. And these discussions, they have two parts. So the second part is the more informal part. And the second part is the one that should take about 30 minutes or more. As you have been seeing, I'm not very strict with closing it. We put all these discussions right before the coffee break, besides because if you are having an exciting, engaging discussion, we can go a little bit into the coffee break. It's not a big deal. So those 30 minutes are more relaxed. Raise your hand if you want to ask questions or make comments. And if you want to ask a question or make a comment, which is very much related to what is being discussed right now, besides raising your hand, wave so that we know that your question or comment is not to open a new topic, but to finish or continue discussing the topic we are discussing now. And of course, Gary and Mirjam, if you see someone that makes more sense to call than the next person in line, just jump ahead and invite that person. Don't wait for me. And of course, you are the coordinators. So that's about 30 minutes of informal discussion. And let me just say a few words about the first 20 minutes. The first 20 minutes, what we did and what we asked Gary and Mirjam and all the people that are giving this discussion is to do as they please. So these 20 minutes are the period of time where slides are allowed. So in this 20 minutes, and people can do everything, whatever they want. In particular, if you want to invite other people to give some small comments and have some slides on while these other people give a few remarks with slides, that's fine if it's during this first or during this allotted 20 minutes of let's call it slide time for preparation of the informal discussion. So that's indeed, for example, what Mirjam and Gary are going to do. They're going to have a few people during this introduction period say a few words. And of course, this announcement doesn't count towards this 20 minutes. So I will now pass it over to them and turn on my stopwatch on my phone and start counting. So thank you very much. And Gary or Mirjam, I don't know who goes first, please take over.
Okay, so I think I'm going to start. And I would, of course, like to thank the organizer for inviting both Gary and myself to lead the discussion session on the progress of constructions of solutions of string theory for particle physics and cosmology, and the directions that may be pointing towards string universality. We have decided to start with the introduction over first 20 minutes by first starting with a status report of particle physics constructions, which I will present briefly. And then in part two, Gary will continue with somewhat broader issues, including also moduli stabilization and cosmology implications. And then for part three, we have decided to give opportunity to the next generation of participants in this program to present further comments and outlook in the order of Miguel Montero, Pablo Soler, and Ling Lin. So let me start with part one, where I would like to present the status of particle physics constructions from string theory. And I will first focus on what is the current state of the art in 3 family standard model constructions on globally defined, primarily Calabi-Yau compactified spaces. So from its original inception, the heterotic string theory was the most promising candidate for particle physics model constructions. And actually later on, it led, among other important developments, to the first standard model, actually minimal supersymmetric standard model with only 1 Higgs doublet constructed by Bouchard and Donaghy. And later on, the broader analysis of big landscape of 3 family standard models was developed using complete intersection Calabi-Yaus, and I hope that Lara will say some more on the stages of those constructions. With the advent of D-branes, the type 2 string theory came in the game for particle physics constructions, and in particular, the intersecting brane constructions had very geometric origin of appearance of chiral matter, where also conformal field theory techniques could be employed. And within this context, one also arrived at the first examples of the 3 family standard models and further landscape analysis. I would say that those models suffer from phenomenological issues. In particular, they typically the chiral exotics there, which to some extent may be associated with the limitations of the type of compactified spaces we could employ to obtain the full gauge and charge matter spectrum there. The last 10 years have seen a revival of F theory for its application to particle physics constructions. So the theory itself reaches to the strong coupling regime, where the nature of the singularities, the geometry of the singularities of the elliptically fiber Calabi-Yau fourfolds determines the gauge structure as well as the full chiral particle spectrum of the theory. For direct particle physics applications of standard models, the Torich techniques actually provided the first example of 3 family standard models with no chiral exotics, and soon after actually led to a huge landscape of quadrillion standard models with gauge coupling unification as an additional bonus. The most recent program is focusing on the leftover aspect of the matter spectra, which is vector-like matter spectra, which are harder to determine in this context, and more recent effort highlighted or developed more quantitative techniques to study the domain of moduli, that would determine the particular jumps in the number of vector pairs, in particular application of the so-called Brühl-Noether theory, and some also machine learning techniques. As far as quadrillion standard models go, there are further complications there because the actual vector spectra is associated with the so-called root bundles, which leads us again to another domain of algebraic geometry. And in particular, we are moving toward the direction of determining really the exact mass spectra and the domain of existence where we have only 1 vector pair of Higgs doublets there. And maybe if time permits, at some later point, Martin Bies can comment further on the outlook of these constructions. So I have sort of put you, in the I brought you to the state of the art of the constructions of particle physics models, in particular 3 family standard models, which were all based on globally consistent, globally defined compact spaces. So in general, these constructions by the definition include quantum gravity, and we expect that these global consistency constructions that keep quantum gravity in play will further quantify constraints on allowed gauge structure, including global one, and the allowed charge particle matter spectrum in this context. And so the ultimate hope in this program is to uncover more and more of universal structures of string theory, and possible the existence of now unknown deeper symmetries that this theory may hold. Of course, in this program, we are really only scratching the tip of the iceberg. And especially approaches are very limited from the top-down perspective, really top-down string theory constructions, and in particular in 4 dimensions, the constraints, universality constraints are extremely limited. As far as F theory goes, the geometric origin of this theory may provide promising range of constraints for structures, including allowed representation for matter spectrum, and some progress has been done by Wadi and company, but also constraints on allowed matter representations in the presence of additional U1s, as well as bounds on allowed number of U1s, and so on. There were also other approaches which I would think may not be as top-down as one would want to have them. And nevertheless, this is a big program, and we've seen some of the nice developments there from a beautiful talk by Irene this morning. Let me also maybe mention some things that there has been more top-down progress in determining constraints on the charge and gauge structures in higher dimensions, and in particular in 8-dimensional cases, where we believe we are very close to the complete classification of global global constraints of all the allowed gauge structures. And what one has uncovered in this context is the important role that higher form symmetries in this effective field theories play, interesting role, and resurrection of string junction approaches, cobordism, the techniques of heterotic string, and so on. And some of it was also highlighted in Cumrun's talk this morning. I hope that also further comments and outlook will be made by Ling, Miguel, and Pablo. So I have tried to highlight some developments in the gauge and charge sector of string theory compactification by focusing on implications for particle physics. However, we all know that there is an elephant in the room right now, which has to do with important complementary issues, not only gauge and charge sectors that I focus on, but there are issues of moduli stabilization, supersymmetry breaking, cosmological implications, dark matter candidates, and so on. All those important issues may not be unrelated. Actually, we expect them to be related. And that brings me now to the part 2 of the discussion, and I should give the screen to Gary. Thank you.
Let's thank Mirjam while Gary sets up the screen share.
I have to stop. Oh, it's already good.
Yeah, it's already good. Yeah.
So you can see my slides, right?
Yeah, just to let you know, we are at the 10-minute mark right now.
Oh, okay. So I would also like to thank the organizers for the heroic effort in putting together this big conference, especially in these trying times. So my task, like Mirjam's, is to give you a little pep talk to warm you up for hopefully a lively discussion. Now, different approaches have been taken to connect string theory with particle physics and cosmology. Traditionally, we start with what we know about the UV and construct models. Then we compute to the best of our knowledge the low energy effective field theories. predictions are then drawn from these EFTs. As Mirjam nicely summarized, this approach has had some successes. And I myself, for instance, have devoted a good deal of my research effort practicing this approach. Now, a question that we often get asked is whether the phenomenological properties of these top-down constructions are genuine lessons from string theory or merely features of specific models. Now, some of these features are certainly model specific, but it's fair to say that there are some general lessons we have learned. For example, the absence of exact global symmetries, restrictions on the gauge and matter content of the power spectrum, a soft UV behavior of scattering amplitudes, and the ubiquity of moduli and dualities. Now, we first came across these lessons through the world sheets, but by now there are new evidence and new perspectives on why these lessons may hold more generally. So the question is whether we can elevate these observations to some general principles. Now, there are numerous examples of what we thought was impossible before the second string revolution that have now become possible. So are we sure that we're not looking under the lamppost? But if we can identify the general principle behind, these are universal lessons that go beyond our current knowledge. The goal of the Swampland program, as Irene nicely reviewed this morning, is to identify these general principles using a variety of theoretical tools, and the list of tools just keep growing. Now, the proposed Swampland criteria are not random guesses. They are often sharper versions of the general lessons we have learned. For example, the weak gravity conjecture and the cobordism conjecture are cousins of the observations that there are no global symmetries. And various distance conjectures are manifestations of the rich duality symmetries. Now, this approach is sometimes misunderstood. So I hope we can take this opportunity to talk things out. First and foremost, the Swampland program does not undermine the importance of constructing top-down models. So explicit string constructions have in the past suggest novel observational signatures that phenomenologists and cosmologists may otherwise overlook. And during the discussions, we can certainly bring up some examples. And having explicit models is also useful for drawing lessons. So serious practitioners of the Swampland would not dismiss a model based on some conjecture constraints on quantum gravity unless these constraints are proven. But with the same fairness, we should not dismiss these Swampland conjectures simply because they are not yet proven. At the very least, we should take them as important warning signs. Now, the Swampland has offered complementary insights that the traditional model building approach does not give us. And I hope we could all agree that finding phenomenological consequences of string theory is a tall order. It will likely require every insight we could get. Now, a general lesson that we can all agree on is the ubiquity of moduli in string theory. Before we fix this moduli, we don't know what is the vacuum. It's associate low energy degrees of freedom and the physical couplings. So stabilizing moduli is a prerequisite for any phenomenological or cosmological discussions. And an important observation that highlights the challenges was made by Dine and Seiber in the 80s. The Dine-Seiber problem can be summarized as the tension between stabilizing moduli and calculability. So it's easy to see because physical couplings are vacuum expectation values of scalar fields that a local minimum can only occur if there are two terms, at least two terms of different order that compete. Otherwise, you have a runaway behavior either too strong or weak coupling. The situation for de Sitter is slightly worse as they require a balance of at least 3 different order terms. Now, if terms of different order compete to give a minimum, why aren't the higher order terms that we ignore important? Now, the large number of flux choices made it possible to find minima at weak coupling. and therefore avoiding this Dine-Seibel runaway. But if the number of flux vacua is finite, as in most constructions, because of the tadpole constraints, the stabilized coupling, while can be made weak by tuning, is not parametrically weak. So an exception is the constructions of DGKT, which find infinitely many ADS flux vacua, because one of the fluxes is not subject to Gauss law constraint and is unbounded. However, careful study of various contributions to the potential shows that parametrically weak coupling de Sitter vacua still cannot be realized. Now, other people in the audience may have other examples that could potentially evade this Dine-Seibel problem. For instance, Eva, we could discuss these examples and how controlled they are during the open discussions. Now, one can also argue that because there are so many scalar fields and not just the dilettante shown here, could the expansion in various scalars conspire to give a discrete family of parametrically weak coupling de Sitter minima? We gave an argument why this does not happen. An exponential fall off is a universal behavior in any direction at parametrically large distance in field space, and not just when we consider the string coupling. So in a sense, it is a stronger results than the Dine-Seibel problem. Now, having no parametric control doesn't mean that there's no control. The standard model couplings are not parametrically weak. But this motivates us to carry out more careful studies of de Sitter vacua, going beyond what have been done, which are mostly at the level of four-dimensional EFTs. And existing de Sitter constructions often involve a balance of classical perturbative and non-perturbative contributions, making the estimation of error challenging. And I believe this will be discussed in more details in tomorrow's discussion session. And Pablo will also highlight some progress made as well as remaining challenges. Now, another example to illustrate that having small parameters does not mean having control on the EFT are the positivity bounds that we heard about on Monday. So let's start with QFT without gravity because the results are well established. So to an EFT, to an effective field theorist, this Wilson coefficients of the irrelevant operator. Okay. So they are arbitrary constants. However, negative Wilson coefficients, no matter how small, would violate unitarity and causality. So this is an example of that small parameters can drastically change the quality of the theory. So gravity introduces subtleties to these positivity bounds. For example, graviton exchange dominates the forward limits of the 222 scattering amplitude and diverges quadratically in the high energy limit. This violates the Froissart bound. And in string theory, this UV behavior is tamed by an infinite tower of higher spin states. And as Leonardo and Simon explained on Monday, this Reggie boundedness is assumed in the S-matrix bootstrap approach to derive quantitative bounds on the high derivative couplings in gravitational theories. And this gravitational positivity bounds were also used to derive the mild form of the weak gravity conjecture. I was supposed to say something about UV sensitivity of inflation, but in the interest of time, I will skip that. So just to wrap up, so when I first started working on string phenomenology, it was considered by some to be the poor cousin of the clan. But the subject has advanced, and it is now interacting actively with other members of the strings family. So I think this shows progress and signs of a very forward-looking field. And in this spirit, we have asked 3 next-generation practitioners to come up with what they think are the outstanding questions. So let's hear from them before we have an open discussion. So I think the first to go is Miguel.
Mm-hmm. Okay, Gary. So thanks a lot for sharing the very nice spotlight with us. Since this is a discussion and we don't want to be overbearing, we'll be super quick. So I have a couple of questions where I think the Swampland can say something very interesting about particle physics. And I'm not alone in here. So we have a poll in the Swampland seminars and open mic events, which is something we've been carrying out for the past few months, and we'll probably be back to it in the fall. And this is the mailing list in case you want to subscribe. And so we asked this question, and you see that most people are interested. They think that the Swampland has best potential of saying something in questions where particle physics talks to cosmology. So maybe next slide. Gary, could you? Yeah, thanks. So I just related to this, I just have two questions, which were raised in Irene's talk this morning. So first of all, there's this coincidence between the neutrino mass scale and the vacuum energy scale. And that's, I think that might be a coincidence for the tantalizing question in which the Swampland can possibly say something. And there's been a number of ideas related to the Arians distance conjecture, no-procedure conjecture, and also this Festina-Lente proposal that we had with Thomas van Riet, Cumrun, and Herben. And I think Gonzalo is gonna talk about this in the Gong show. And finally, there's an important question everywhere in the Swampland research, which is what is the role of discrete parameters or discrete symmetries? Something like the Wiggerati conjecture doesn't tell you anything about the IR. If you're not able to say, you say there's a light particle, but you say what its charge is, then you cannot, it doesn't really constrain the IR. So we really need to find arguments to constrain this value of n. And this problem is pervasive, is related to the order of discrete symmetries in the Swampland, and also to the issues of scale separation, as you can see in that paper in the bottom. So Pablo.
Thanks. Gary, can you? Thanks. So I want us to make some brief comments and pose some questions about string theory and cosmology. Gary already suggested some of the abstract problems, but I want to focus on two particular technical aspects. I will focus on those that were most popular in the Swampland poll, which have to do with the Sitter constructions in string theory. And in particular, I will focus on the KKLT construction. And I want to bring up two technical aspects that we've made progress in the last few years. One where we've clarified some potential problems, and one where new potential problems have been brought up. The first one is an apparent puzzle that seemed to appear between the four-dimensional description in 4D supergravity of the KKLT effective action and its avatars in the 10-dimensional action of type 2b. We found out that that potential class was just a consequence of not having full control of the D7 brain action in up to quartic order in Gagino, which played a crucial role in KKLT. So in that regard, I think that's one particular possible puzzle where actually the path has been clear for KKLT. But at the same time, new potential problems keep coming up. So I'd like to bring up in particular this potential one of the singular bulk problem that says that generically in KKLT compactifications in the regime where one can lift to the sitter, the bulk does not look like a smooth geometry, but it becomes singular in an order one chunk of the bulk. There's many more progress and recent insights that we'll be covering the rest of the discussion, but I just want to ask the audience how they feel about these technical problems towards the sitter or also towards the scale separated ADS, whether they will be cleared or whether they will go towards more swampy regimes. Ling.
Okay, thanks. Yeah, so I will just make a few short comments about the universality or the lamppost principle. So as Irene introduced in her talk, the idea of universality or the lamppost principle is that all consistent effective descriptions of UV complete gravity is realized in some corner of the string landscape. And if we want to prove that, and at least for a class of theories, then I think what we should do is really scrutinize the physical arguments that correspond to the boundaries between the landscape and the swampland by inspecting the geometric constraints that prohibits us to construct these theories that lie in the supposedly swampland. And I think the geometric boundaries, constraints that in part shape these boundaries really can teach us about perhaps yet unknown physical consistency conditions. Another interesting point that also Irene mentioned is that some features of consistency quantum gravity seem to appear also in CFTs, for example, the CFT distance conjecture. Another class of models that has similar kind of structure is rigid structure is indeed the 60 superconformal field theories. And so far, we don't know of any concrete 60 theory that does not have a string theory realization. Yet, of course, there is by no means settled that if this is actually a physical principle behind this exclusiveness. So finally, I think it's a good time now to maybe explore some synergies between the Swampland kind of approach and maybe some of the ideas that was discussed in the Monday session on bootstrap and positivity, and perhaps also holography, in order to maybe find really some deeper underlying structure of all these conjectures in Swampland. So yeah, this is just some of the ideas that we had. Yeah, we will now let the public talk and share their ideas and comments. Thank you.
Okay, let's all thank all the participants in this first introduction, and Gary and Mirjam and Ling, Pablo.
Thank you.
So yeah, let me just, before opening the floor, also remind people that tomorrow there are two discussions that are not unrelated to this one. And in particular, there is one by Eve and Daniel on cosmology, and then in particular on string cosmology, and the second one on constructions of the sitter by Shamit and Fernando. So yeah, I would suggest perhaps that yeah, if there are things that if you run out of time, if the sitter, some of the sitter things could move to tomorrow, so yeah. So please raise your hands.
Maybe there is just in general, yeah, there may be some issue, to focus on some of the aspects of particle physics directly, charge degrees of freedom, string theory. Maybe I see Martin would like to say something to maybe complete with a word or two what I was saying. Martin?
Yeah, indeed. I wanted to comment on the recent work on root bundles that you already mentioned. Yeah, I see you have a nice image of root bundles there. So I wanted to make a comment on that. First of all, for people, it might be interesting to know that root bundles can be thought of as generalization of a spin bundle. So this idea becomes, in a sense, quite natural. Comment number two is on a smooth curve. These root bundles are fairly hard to construct, and the image that Mirjam is showing right now is actually on a very nodal type of curve, where we actually have a means to construct these bundles. That's then called a limit root, and was originally introduced by full mathematicians to illustrate this. The image is maybe good to see. And so the complexity in this sense only becomes that of somewhat combinatorial nature, namely placing some weights in this diagram. So this is quite nice to see that this fairly complex task becomes a quite natural or combinatorial one. And maybe also towards open questions in that regard. I guess you should raise two questions. One is these constructions, they are of course in very nodal curves, which are not per se physical. So the one thing that we are currently working on is transitioning from these very nodal geometries to the generic physical ones.
Even like we are looking at the wrong file, I'm afraid.
Yeah, but by the way, we should not be looking at any files, no? This should be, we should, I would prefer, yeah, right now we should, if we could not see files, if we could just.
No, it would be better if you turn it off, please.
But I thought I did point out, yeah, maybe you should just.
We saw the picture, we saw the first nice picture,
yes.
So that was good, but maybe just seeing Martin would be enough.
Yeah, maybe I can fill in for the picture. Okay, so one more open question in that regard that I should mention is these constructions on the nodal curves are in a sense bottom up, so we know very well what we're doing on the curve level. But of course, the full answer from string theory is we're taking the 4D theory or the 3D theory, at least the full F theory construction in this case, and take it down to the curve level. And that, of course, is expected to give some limitations on what root bundles you can actually take. That step, taking it from the threefold potential in M theory down to the curves, telling you exactly which root bundles to take, is one of the conceptual challenges that we are going to explore in the upcoming future. So that's the comments that I wanted to make. Thank you.
Thank you. Any other questions, comments? Yes, Ignatius, would you like to comment?
I have a question, actually.
Okay.
With this, you mentioned in the beginning the historic history of string phenomenology, starting from various models, starting from the heterotic, going on to deep brains, F theory. So my question is, what have we learned in practice with this, after this, all these years of model building? Of course, we learned tools, different tools to use and construct models. But did we succeed to go closely to the standard model from, let's say, the very beginning times of the heterotic string?
Well, yeah, I thought I gave you a bit of a complementary advances, right, in all those directions. I personally believe that the geometric tools have not only been advanced, but are becoming also very powerful for us to determine large, as you know, to be able to construct, engineer really huge landscapes, right? It's not only a question, can you construct a model as an assignment, but really to explore the broader landscape. So the geometric techniques, in my view, have become very important. And in particular in F theory, with toric techniques, we are able to explore many more constructions of that type. Now,
I agree with your assessment, but my question was how close we went to the standard model at the end.
Right. If you look at, so the question is, at what level are you asking this question, right? If it's an assignment, can you construct the model that has the exact spectrum of the MSSM, which was somehow the goal in this program? Excuse me.
So I see that Sandip and Wati have raised their hands for a while. Maybe we could get to questions or comments.
But maybe I should just wrap it up, right? Okay, sorry, Gary. So the point is that actually, as far as the exact MSS spectrum goes, right, there are specific issues in each of these constructions. We personally believe that F theory may provide us a bigger landscape with exactly MSSM spectrum because the geometric techniques are more advanced. Now you want to ask other questions like, are all the Yukawa couplings working? You know, what happens in the issues when you include the Moduli stabilization? Those are all big questions that we don't have better insights right now. But I thought just the spectrum and the exact one, I think we have advanced with geometric techniques and made the progress in that, which I think is per se an important thing because the devil, as you well know, is always in the details. Okay, maybe we should let Sandip, Gary, why don't you go ahead?
Yeah, so Sandip, please.
Okay. Yeah, no, thanks a lot. You know, I haven't been working actively in this field for some time. So this is more just to also find out from you all about where things are. But even, you know, whatever, 10 years, whatever ago, when we worked on flux compactifications, it was already clear that, you know, quite generically, even with supersymmetry, there were vast classes of compactifications which were very different from Calabi-Yao's. They were, you know, they could be complex manifolds with torsion, that was known, but they could also be manifolds which were not even complex. You know, they did not have an integrable complex structure and so on. And that seemed, in a sense, very exciting because it opened up these huge new classes of manifolds to study. And I just wanted to know where things are in terms of understanding those manifolds, their moduli spaces. Are there the analog of, you know, Yao and Calabi's results and so on, where the field stands? Thank you.
Right. So I think there are efforts not only in extending the space of compactifications, but also go more into a more microscopic constructions. So I think the question that sometimes people would ask is, having a sketch, like all these branes, fluxes, wrapping around cycles, having a sketch does not mean that we are guaranteed to be able to put them together to give the proposed four-dimensional effective field theory. So I think as Pablo alluded to in his short presentation, there have been a lot of efforts trying to lift all these four-dimensional effective field theory ingredients into a more microscopic 10-dimensional description. And so when we have this, when we up our game, we may be able to quantify more precisely the type of corrections that Dine-Cipher problem typically suggest that they are there. Right? So one would have to be looking more microscopically into these constructions, or maybe Pablo or Miguel could comment further on that.
Well, I think it's an interesting question, but also I think it's related to something Cumrun said before. How complicated are the models that we want to tackle first? If we want to achieve something something like a positive CC, if we fail in Calabi-Yau, then next take a more complicated setup and step by step, because otherwise we end up with many models and none of them fully understood. That's, I don't know, I have a finite amount of time that I can spend on each of them.
Okay.
Right,
So
okay.
maybe in the order, it may not be exactly, right, focusing in one direction, but maybe Wadi should have a chance to ask questions, comment.
Sure, thanks, Mirjam. Actually, I just wanted to add a little bit to what you said, Mirjam, in response to Ignatios's question about, where have we gotten with this? And you commented, Mirjam, I think very accurately that F-theory gives us, this very large range of things. I just wanted to add a few comments to that I think some of the reasons that this, in particular, this F-theory approach and combining that with some of what we've learned about string universality and Swampland things has really given us some new insights is, first of all, that F-theory really gives us a global connected view of a very large class of vacua. And this is most apparent, for instance, in 6 dimensions, where all the different elliptic Calabi-Yaus that F-theory uses are connected essentially into a single moduli space, connected by various extremal transitions. And that huge moduli space with hundreds of thousands of branches matches very closely in the sort of string universality Swampland story with what we see from 6 dimensions. So from F-theory, we see, first of all, a non-perturbative, but also a global picture that, at least in 6 dimensions, seems to give us a very large part of what we know is possible in quantum gravity. And so extending that to 4 dimensions, where we really have a connected set of geometries, even though there's a superpotential sitting on that, there's still a connected set of elliptic Calabi-Yau fourfold geometries, again, all connected by extremal transitions, so forming a kind of a global moduli space. And I think that gives us also the ability to ask questions like, what is the naturalness of different constructions of the standard model? I mean, Mirjam mentioned there are these quadrillions of constructions through certain kinds of tunings. There are other ways you could realize the standard model. And I think we can begin to ask quantitative questions about which of these constructions require more fine tuning and which are most natural in this very large connected landscape. So I just wanted to add those points.
Yeah. Well, thank you, Modi,
Thank
for
you.
recording so nicely. Yeah, what I try to point toward. Thank you. So, Gary?
Next is Thomas. Right. I think you are the next. Thomas Van Beet.
I'm here. Can you hear me?
Yes, I can hear you.
Yeah, thanks. I have more a question to the audience. Since we started talking about, the history, where are we going? What did we achieve? The thing that I always find a bit surprising is that many of us do all this highly technical work on finding, spectra, kind of gauge groups. But the weird thing for me is that shouldn't step one be, in the end, always moduli stabilization, finding the vacuum? And in particular, a very crude and simple criterion is, can I even use an effective field theory? And to be able to use an effective field theory, one of the requirements is what we call scale separation. Okay, so the very simple fact that I can stabilize extra dimensions, I can hide them from my view, is such a basic thing if you look at our own world. And the fact that there was even a conjecture by some of the people here suggesting this could even be impossible, say for ADS vacua, to me shows that one of the most fundamental things about string pheno, one of the most foundational things we don't even agree on. So isn't it a bit strange that as a subfield of string theory, there's so little focus on this? I think it would be great if at some point the majority could say, we achieved a consensus. We say there's no doubt we can reach, scale separation or not. Because I think one of the things I wanted to add, and then I'm done, is that this whole question of, say, something simple as moduli stabilization and scale separation and the use of effective field theory also relates to a fundamental choice we have to make. Do we believe that, compactifications are the way to go? Or is it maybe, brain worlds? Maybe brain worlds are, they seem to be really two different things. And I think it's important to decide between the two. What would be the way forward? And I feel these are such simple questions, and they're sort of in contrast with some of the highly technical aspects, say, done by the F-theory community. I find it a bit surprising. So I'm just interested in somebody's opinion on this. Thank you.
Okay.
And you take it.
Let me just say a non-physics thing. If people can keep their cameras on, I think it makes it feel more cozy. So if you can, of course, if your internet allows, keep your cameras on so that we feel like we're all in the same room.
Can I just make one comment about what was just said about ADS non-SUSY and just add to it if I can, or I can wait?
Please.
Just 2 minutes, which is, isn't this a great question to try and address with the Bootstrap program, which is, can you get a non-supersymmetric ADS with a large gap? It seems like the simplest non-SUSY kind of question of some relevance to phenomenology we could go after, using the Bootstrap. I just wanted to ask you all what you felt. Is it something that could hopefully be tackled using those techniques? Sorry.
I think Thomas would be the one responding to your question.
I just want to add to what Sandeep said that, well, there's a chunk of people trying to do this. It seems to be very complicated. But let me add that the question that you're asking is not particular to non-SUSY ADS, right? So this question of scale separation, or just using effective field theory that it's allowed, so scale separation, you can ask that question for supersymmetric KKLT, for instance. And we should try to find the CFT dual to KKLT, at least a supersymmetric ADS one. And the same for these DJKT solutions. And people are actively trying at the moment. And I think the main hurdle is this observation by Polchinski and friends that, you can sort of, bootstrap bounds can become trivial in a way that you always kind of get they always can get consistent with some kind of a naive effective field theory that I'm writing down. It doesn't mean that it will not work, but this I think is the main obstacle that people are having in this subfield.
Thank you.
Okay, so
I
think Eva is
just
next.
one thing, Miguel was waving, so I think it probably means that he has a comment related to precisely what is being discussed.
Okay.
That's right. I just wanted to make a quick comment. So I really like Sandeep's idea. And one context in which we maybe can make a lot more progress and sidestep a little bit the objections that Thomas pointed out is in the context of ADS tree, right? If you have an ADS tree scale separated vacuum, and I think Thomas and friends constructed examples of this by mimicking the DGKT logic also on type 2A on a G2 manifold. So that's something you can actually try to study from the dual CFT point of view using all the techniques that we have that are exclusive to CFT2s like modular invariance and stuff like that. So that's probably a promising element.
Thank you. Thank you very much.
Okay, so I think Eva is next.
Okay, sorry, I'm not using my video because I'm having internet troubles today, which I'll solve by tomorrow, I hope. So there's a lot to respond to here. So one of the young people, I apologize, I forget everybody's name, raised the question of what the status of KKLT is. And as someone who's followed that subject a lot over the years, let me add that I think with this last question that was raised about, are there singularities inside of the manifold? I think there was a rebuttal to that by Jakob Moritz. And also, I think the assumptions behind that were strong, that is, they assumed that sort of all the charge was coalesced in some region of the manifold, whereas it could be distributed much.
I'm trying to wave my hand, but I can't.
Yeah, we stopped hearing Eva for a little bit.
Right. So thanks, Eva, for the comment. I agree with your comment. Can you hear me? I am hearing some echo. It's okay.
I think there was some connection problem.
Trying to complete
So Sorry, Eva, if you can hear us, your connection, I think, is not cooperating. I think it's not possible to understand.
Cool.
Oh no.
Oh, now we lost.
I think we lost
So
her.
maybe in the interest of time, Pablo could say a few words, and while we're waiting.
I was just gonna say that I agree partially with what she said. There's some work, and I think the authors are not here, unfortunately, of how to possibly relate this KKLT singularity. But I don't know what is if that's the way to resolve the singularity, or what would be the final status of our understanding, whether that would change our understanding of the effective field theory of KKLT or not. But I do agree with another comment she made, is that these seem to be genericity questions that would say, like, if we treat the D3 charge homogeneously, then it's difficult to reproduce the standard picture of KKLT, but it's not impossible. So maybe this will just cut out chunks of the landscape, not. And that was my question, whether we believe these problems are generic problems, or that will be resolved simply by narrowing the landscape of possible compactifications, or truly singular problems that will change our understanding of KKLT. And I agree with Eva that it seems to me that there's some notion of genericity in these problems. I think this will be discussed in more detail tomorrow. It's probably more appropriate. I brought it up because the discussion is going to be at my 3 a.m. time here in Korea, so I'm gonna miss it, unfortunately. Sorry about that. But that's.
I think there are two parts. I think there are two parts of that issues. One is whether the singularity is resolved, and the second part is whether we have control of the low energy effective field theory. And it's true that the singularity that was pointed out in the reference that you cited was there was a proposal to resolve the singularity, but I think it remains to be shown that the low energy effective field theory of KKLT matches with this strongly corrected bulk. I think this is an open problem.
I believe Sandeep was waving, so maybe he has a comment related to precisely.
Please.
I just wanted to say, I didn't want to get into KKLT because I thought we have a whole session, and maybe we'll do that. Since you brought it up, I mean, this singularity issue, as far as I know, is in some particular way to arrange the charge and so on. At least I'm not convinced that it's a generic feature of the general KKLT mechanism. Now, if you like, we can talk about it later. If you say generically, the way you do the KKLT construction always gives rise to stringy curvature regions, and there's a proof of that. Okay, I at least don't know of that. Okay, so, but we can perhaps postpone it for tomorrow. And
it also depends on what you mean by KKLT. Do you call the bulk that is strongly corrected KKLT? If so, then that's a different problem. So. But as you said, there would be a more detailed discussion about specifically about the zeta constructions tomorrow. We could continue that on as well. And I think there was a hand raised by Ander.
Irene?
Or Irene? Irene, I think Irene is first.
Yes. Irene, maybe you should comment.
I don't mind who goes first. Okay, yeah, I mean, I had a general comment about what we are discussing, because it seems that people are worried about where are we, how much we have learned, how useful is all these approaches. And I personally believe that we are at an inflection point, in the sense that we have learned a lot about string compactifications, how to construct some things. But I think it's the moment to gather all this information and, of course, continue, but also gather this information and try to extract what are these lessons and in which lessons quantum gravity really matters. So I don't think it's just a matter of whether we get the standard model, but try to identify those points in which quantum gravity have something additionally to say beyond quantum field theory and so on. And try to connect these general lessons with other approaches like ADS-CFT, positivity constraints, and all the tools that we are learning from other fields. So I think sometimes we get, I don't know, lost in the technicalities. But yeah, I don't know, I would like to bring back like some of the questions that Miguel, Pablo, and Lynn suggested that where quantum gravity matters. Does it matter to engineer hierarchies, natural and usus? Does it matter to understand scale-separated vacua? Is something more difficult? It's something easier in string theory, or the sitter? I mean, of course, it's also a clear topic. But where are the? Let's try to identify like some simpler universal things that we don't know yet how to engineer, and that quantum gravity can be behind that. No? And I think this is the inflection point that we are observing, and that it's obvious also from all the talks in the string phenomenology conference. I mean, that there is a change of paradigm in that respect, and that we try to open and connect with other fields. So, yeah.
So
thank you, Irene.
Wadi, I'm sorry, but Wadi seemed to have, you have your hands up? Yeah, still for some further comment, or?
Oh, no, sorry, that's just an artifact. I forgot to take it down.
Apologies. Then Cumrun, I saw rose a hand. Yeah, please go ahead, Cumrun.
Yes, just a comment. I think that Thomas actually reflected the view I have also, that first of all, finding stable vacua in string theory is extremely important. And to me, this is the single most important thing we should be doing in string theory. The amount of effort, I think, by the research going on in string theory is not commensurate with the importance of this question. I think a lot of effort is going on to questions of black hole holography, which is all fine, but we want to connect ultimately to our universe, and this is not getting us that close to that question. I think the community should redirect itself, at least to a great extent, to get tools to answer these difficult questions. Clearly, we have a lot to go. Clearly, it's difficult, but clearly we have begun to answer some of these questions. And I think that without more of the community getting engaged, that will be unfortunately going to be delayed. So I want to make this appeal to our string community to put more efforts in the directions of trying to connect to string theory toward the real world, which is not happening, unfortunately, in most research.
Okay. Agreed.
I think Eva is back.
Yeah, hi, can you hear me?
Yes.
Can you hear? Okay, thank you. I just wanted to say a couple of more things regarding this kind of meme about scale separation. It really is related to a very simple plot that Gary had, the one where he referred to the Dine-Seiberg problem and how you need the three-term structure to get de Sitter space, which has been known as that was the first thing we noticed in studying the cosmological constant 20 years ago. And it's that three-term structure with a large number that allows the three terms to compete that enables a tuning of the four-dimensional Hubble to be weaker than the internal curvature. So that it's just that. It's really a dumb, simple, mechanical thing. And so that's how it works in all the models, and that's why we get scale separation. One thing to say about the difference between de Sitter and anti-de Sitter is that there are some really interesting ironies in the subject. So for some purposes, de Sitter is simpler. Here's an example. In anti-de Sitter, if you have a kind of landscape, okay, if you have decays that are available, well, they hit you in an ADS time. And that's because of the asymptotic volume contained in ADS. However, in de Sitter, a metal stable potential energy gives you a solution that indeed lasts an exponentially long time. So in that sense, the de Sitter metastable solutions in the landscape are exponentially more stable than the corresponding ones in anti-de Sitter. But in any case, the separation of scales, in my view, is really a non-issue. It has to do with the three terms. If you want to know what the large number is in the various constructions, it's large D in the original constructions. In the power law context, it's W naught in the KKLT constructions. It's large genus or other parameters in hyperbolic spaces and hyperbolic compactifications. It's various topological quantum numbers in the large volume scenario. That parameter is known, and that's why we get scale separation. It's not too hard to understand. The last thing I want to say is the cosmology session, we're planning to kind of keep it more down to earth. It'll be more about the sort of clear UV sensitivities that Gary skipped over. So if people do want to make sort of grand statements about attempts at no-goes and so on, I think this session would be the one to do it in. One thing I would ask though is that if you make such a conjecture, it be consistent with all of the ingredients we know and all the models that we have. So in that spirit, for anything to do with cosmology, inflation, or de Sitter, it's important to incorporate the leading terms in potential energy. And that includes the D minus D critical term and the curvature term, which is typically positive potential energy, along with all the other sources that people talk about. So for any kind of no-go theorem, those must be addressed.
So we have the discussion leaders for de Sitter construction tomorrow here. I think Fernando is here. If this is going to be discussed, maybe we could move on to the next questions. Otherwise, we could keep going for a little bit. I don't know how much time we have.
Yeah, as I said, so if we are going well, there's no, we can go for a few more minutes.
So for instance, I suppose Shamit and Fernando will go through some of the issues that we are discussing today in more detail. And maybe we could go to the next who asked questions. Is that Ander?
Ander, yeah.
Sure. So I have a question following a bit what Thomas started and Cumrun followed. Well, I've been on board in the field for, I don't know, 10 years or so. I have the feeling that, say, 20, 15 years ago, that there was more activity of people working, well, trying to contact the string theory with observations. And I have the impression that some people, well, maybe took another direction, maybe because they found something more exciting, or, well, I'm actually wondering, I would like to ask the more experienced people that maybe they were working in this field, why they decided to take this direction. Because I had the impression maybe that it was that, I don't know, well, there was no significant progress, or they felt there was no significant progress, or, well, whatever the reason was, I wanted to ask more experienced people what the reason was.
Oh, yeah. Look for someone experienced, was doing phenomenology and is now doing something else.
I mean,
there are plenty here, so I'm not one of them.
If anybody's willing to answer or say something.
Well, I don't know. I'm certainly guilty of that. I'm really guilty of that. But I don't know. I mean, you don't listen to the older people, actually, is what I would say. They're obviously wasting their time. But I don't know. I mean, others should say, others are more distinguished. But I don't know, the field, in a sense, new questions come up and I mean, these are very important questions, but you need an angle to attack them. And for example, for de Sitter, it just seemed worthwhile to try and address some of the conceptual questions, which are also tough. I don't know. I mean, I don't know. Don't listen to the older people. They're wasting their time.
Advice?
Sakura is young and she wrote in the chat. Sakura, don't you want to chime in?
Say something. I mean, I can say something.
I actually don't really want to say a lot because it might have a lot of background noise, but I think there's perhaps another question that you're really asking, which is to what extent do actual phenomenologists care about this? And I think if you're doing string phenomenology, you need to ask yourself this question, right? Am I actually doing something where a happy person would actually go out and seek out those results? And I think for some of these things, this was certainly for a very long time the case, but then with sort of the death or the almost death of supersymmetry, maybe that has stopped a little. And so I think that's certainly a factor, and perhaps other people want to comment.
Yes. There's a revival with the Swampland program on that, no?
Yes.
It's even more phno.
Absolutely.
Yeah.
I think he was asking a question about people building models like, we used to do in F-theory.
So I think the phenomenologists are paying much more attention to string theory these days, precisely because these questions that are arising in Swampland are very close to things that they are interested in. So that actually brings an opportunity for us to connect with phenomenology as well as bring their insights into it. So I certainly think that that's a good golden opportunity for our research, but the questions are still tough. Getting the exact model and so on is a secondary question right now, in my opinion, because even the basic questions we're still not debating, whether we can get the minimum and so forth. So there are these kind of questions we really need to focus on and try to come to some kind of better understanding.
Maybe Dimitris and then Nathan.
Hi. So I have a sort of elementary question of principle, really. So suppose we have a large enough sample of string vacua, whatever that means. I'm wondering, what do we do with them? I mean, should we think about summing over all of these saddle points to get the full quantum gravity path integral? And how far can we go in that direction? Suppose we did have all the saddle points that are relevant, or whatever that means. I mean, would we actually think about summing over them? And if so, to what extent is a specific vacuum that important?
Well, why would you want to sum over it? If you find all of them, then I would check which one of them looks like our universe, and we're done. So I think in some
Well,
sense,
the thing is that if you have a path integral over some theory, there was this talk actually by Neil Turok that got me thinking, that he was saying that you can rewrite the full path integral as a sum over its saddle points with certain phases. And that was quite a generic statement.
oh, you're talking about the finite action processes. If you choose a background, to go to any other one, typically when you fix the background, might be different. So
you fix a boundary conditions.
Yeah, you fix the boundary conditions.
And then I'm wondering whether we should really be integrating or summing over
there's
all
no
saddle points.
Of course, those questions that you're asking will become important for early cosmology, and whether or not there's, to what extent our space is compact, to what extent we can shuffle from one to the other, and all that. But I think for present stages of the universe, you just pick the one you're ending up with if we had all the answers like that. Because if you have a non-compact space, there's no sum, right? There's a super selection.
I don't really understand where your reasoning comes from.
Super selection, like, well, how do you freeze the web of a field in dimensions bigger than 2? You cannot integrate over the web of the fields. You freeze them. Why? Because of the infinite action that you need to change them at infinity.
Sorry, I'm a co-host, so I can't raise my hand. But just on that question, I mean, I think it's an a point that hasn't really been made that connects with that question is that, I think it's probably ultimately very important that we understand how to actually get some microscopic kind of framework where some cosmological solution can be embedded. And, if we had that, then this could help answer these questions of, what is playing the role of, some kind of gravitational path integral or whatever. We have that for asymptotically ADS. We don't really have cosmology, but I think if we do, then
yes,
that will help answer all these questions.
Yes, cosmology is a golden opportunity, I think, for string theory.
Maybe Nathan still, yeah.
Nathan.
I know how to wave my hand. I think the question was answered about why people left phenomenology, but I mean, I think it's something that older people maybe know, that when there's a new experiment that's going to be built, I mean, there's a great motivation to do phenomenology. So, I mean, I think I remember when the super collider was supposed to be built, there were lots of people moving to phenomenology, and the LHC, I think, inspired lots of people. And as Cumrun said, when there are new cosmology experiments, I think lots of people from string theory will go try to find predictions for that too. So that was all. I mean, it's kind of obvious.
Right. I think we would take string phenomenology to include not only particle experiments, but also cosmological experiments. There are many exciting possibilities that we will hear more about tomorrow.
Okay. Sorry, I see Eva have hands up, but maybe we should let Louise make a point. Louise Ibanez. Louise?
Yes, I'm going there.
Yes, we hear you.
I just wanted to make the comment that I think that phenomenologists care about string and string phenomenology. They have borrowed, particularly beyond the standard model phenomenology, a lot of ideas from string theory. They are eager to learn new ideas coming from our field. Remember extra dimension, remember now the constraints on action couplings or in action inflation, etc. in cosmology. And I think that's I mean, new ways to understand the hierarchy problem. They are really following. I mean, the phenomenologists who are more on the theoretical side, but there is a large fraction of those. And I think with these new Swampland ideas, they are also very attentive because perhaps we can learn new ways to understand the hierarchy problem. I also believe that the story of the neutrino masses and the cosmological constant could be a very important hint. I find it interesting that there could be such a connection. And I think that we should focus, if ideas like the Swampland ideas come with a very definite prediction, like for example, the neutrino, lighter neutrino mass is such and such, that would be very important for the whole program. Or, for example, understanding strong CP problem from these ideas or other naturality problems, or a good simple explanation of the hierarchy problem. Why really quadratic divergences really do not matter when analyzing the mass of the Higgs, for example. If the fact that the scale of supersymmetry breaking, for example, the fact that the standard model without supersymmetry becomes unstable at 10 to the 10 GeV or so, what's going on there? String theory can tell us something about that, the stability of the standard model. I think the string theory has the potential to give, is a natural source for new ideas to understand, to make contact between quantum gravity and the real world. So I'm still optimistic.
We like your optimism.
I would suggest either we conclude with an optimistic note. Eva, is your comment related to the sitter or something? If it's the sitter, maybe we would postpone for tomorrow and end on an optimistic note, I would say. If not... it
was on the subject of supersymmetry and should that cause people to leave the field? Was that Sakura's question, basically? Sorry, I do have the internet problems. Anyway, I think that that's a very, very interesting point because there's kind of two narratives in the field. One is kind of bottom-up supersymmetry, grand unification, et cetera. And the other is, well, what do we generically have in string theory? And almost everything is not supersymmetric at low energies. I mean, but those are really 0% of the string backgrounds. And make no mistake, the ones that are not as supersymmetric are perfectly controllable by standard methods of physics, the things we do in empirical physics all the time, including but not limited to perturbation theory, numerical method, mathematical theorems, et cetera, et cetera. So I find this question about supersymmetry extremely interesting for this reason, because there's a tension between these two points of view. But from the point of top-down string theory, there's nothing that forces us to supersymmetry. And if we look, in my view, if we look just honestly at the space of string backgrounds, it works quite in the opposite way. So it's we have generically positive potential energy, good for cosmology, and generically we don't have low energy supersymmetry. So it's perfectly consistent with phenomenology. And yes, regarding the connections to cosmology, which already exists, we'll cover those tomorrow.
Thank you.
So maybe on this note, we should wrap up this discussion, which actually went quite over time. So
yeah,
that's
great
a good
fun.
sign too, right? And
thank you very much, Mirjam and Gary and everyone.
Thank you.
Thank you.
Bye.
Thank you. See you in 10 minutes.
Bye.
Okay, looks good, Jim.
Okay, so it's 1:40 in Brazil. So I think we can start the last section of today, which is going to be our Gong show session. So these are going to be 10 talks of 5 minutes each. And the first one is going to be Alec Bedroya from Harvard, telling us about thermal de Sitter and the Swampland. So Alec, you have 5 minutes.
Thank you. Let me start by thanking the organizers for organizing this great event and for giving me the opportunity to talk about my work. So today I want to talk to you about the relationship between thermodynamic aspects of de Sitter space and Swampland conditions. Next slide, please. Right, so let me start with stating an observation that de Sitter space seems to have some unique features that seems to be different from ADS or flat spacetime. Let me just mention a couple of them. First one is that it seems to be more difficult to construct stable de Sitter and much more difficult to construct stable de Sitter in string theory. And the second one is that de Sitter space seems to have unique and strange thermal properties. And this is something that we'll circle back to later in the slides. I think whenever you have unique features, there should be some connection between them. And interestingly enough, around 2 years ago, in the context of one of these Swampland conditions called the transplant consensorship conjecture, or TCC for short, a time scale that naturally appears in the conjecture was equal to scrambling time, which is a time scale that is very natural in studying the thermodynamic aspects of de Sitter space. And this is what I want to talk more about in the slides. Next slide, please. So let me start with a very brief review of what transplant consensorship conjecture, or TCC, is. So the statement of the conjecture is that if you start with Planckian fluctuations, the expansion of the universe cannot be too fast and too long such that these Planckian fluctuations stretch beyond the Hubble horizon and they freeze out and classicalize. And you can look at the paper for a brief review of the motivations and consequences of this conjecture. But just to give you a universal consequence of this is that when you apply this conjecture to different different realizations of de Sitter space, whether it's metastable de Sitter, unstable, or quintessence model, in all the cases it seems to suggest that something significant must happen in time less than 1/h log 1/h. And this is a time that I'll be referring to as TCC time. And just to mention
Sí, pero el problema es que ves el chat. El chat tiene cosas que no tienen desperdicio. Hay una discusión de qué tiene el chat también. Por eso entraron, bueno.
Someone's not. Okay, thank you. And so just to mention a couple of highly non-trivial evidence for this conjecture from string theory, it seems that TCC implies the de Sitter conjecture and the distance conjecture with specific, sharp, explicit numbers in the asymptotics of the field space. And these inequalities have been verified for various string theory constructions. Next slide, please. So that was the Swampland side of the story. That was the Swampland side of the story for de Sitter space. Now let's talk about the thermodynamic side of the story. So there are two ways that we can understand thermalization in de Sitter space. One is in flat slicing coordinates, and the other one is static coordinates. So in flat slicing, we can understand thermalization as in the following way: as the modes are expanding and they go beyond the Hubble horizon, all of them are set to be in the Bunch-Davis vacuum, which is well behaved at small scales and is at thermal equilibrium. And so eventually the whole Hubble patch will be at thermal equilibrium. And in static coordinates, the way that we can understand this is that there's a stretch horizon sitting close to the Hubble horizon, and that stretch horizon is interacting with the interior of the static patch, and eventually everything thermalizes. And these two approaches agree on the time scale for thermalization. The time scale that we get from both of them is 1/h log 1/h. Next slide, please. Right. So from the equality between these two time scales, and from other observations that you can look in the paper to see to see them in more detail, it seems that various Swampland conditions are suggesting that de Sitter space cannot be viewed as a viable thermal equilibrium background. Now, this doesn't mean that it doesn't have any statistical interpretation. And I just want to mention a couple of strange features for de Sitter space when you do view it as a thermal background. The first one is that the Hubble temperature is so low that the number of particles in that thermal background in the whole observable universe is of order of 1. And for instance, the number of photons. And secondly, the energy of those particles is so low that if you want to measure it, you would need an apparatus of the size of Hubble, like the observable universe. And I just want to end with a small advertisement for an upcoming work that we think that there's a fundamental tension between unitarity and de Sitter space when it lives longer than TC time. And I'll be happy to take questions. Thank you.
Time is up. Thank you. Okay, so for questions, so you can either write on the chat the question during the talk or raise your hand now. So, okay, so Cumrun is asking, what is the tension with unitarity?
Right. So yeah. So the tension seems to be that if we want to describe the physics in the language of de Sitter complementarity, if we want to describe the physics in the static patch with a unitary time evolution, then there are bounds on how fast the entropy must grow, and it seems that like we can, if de Sitter space lives long enough, longer than the TCC time, then we lose some information and we can violate those bounds that come from unitarity.
So the other question is, Sayatan is asking, how have you computed the thermalization timescale?
Yep. So that's a very good question. So in flat slicing coordinates, you can compute the thermalization timescale. Like you can look at thermalization as Planckian modes exiting the Hubble horizon, and you can calculate that how much time it takes for Hubble, like Planckian modes to exit the Hubble horizon. And that's exactly where the TCC timescale comes from. And people have done that also in the context of de Sitter complementarity. They compute the scrambling time, which is, I mean, you need the thermalization timescale to be greater than scrambling time, and that also gives the same timescale, 1/h times log 1/h.
Okay, so thank you. So let's.
Oh, and yeah, and please also, yeah, the paper of Gary with Lars also gives an excellent explanation for that. Sorry,
so,
thanks.
Thank you very much. So next one is going to be Eduardo Gonzalo Badia from Madrid, from Instituto de Física Teórica, who is going to tell us about constraints on the standard model from ADS conjectures. Eduardo, are you there?
Yeah. Okay.
Good.
Okay. Thank you. So thank you, and thank the organizers for putting together this very nice conference. It's a great honor to present my work in the Strings conference for the first time. So my talk will be based on work with my supervisor, Luis Ibáñez, and collaborator, Irene Valenzuela. And can you please go to the next slide? So I will start with two questions. First one was already introduced by Miguel and also by Luis in the previous discussion, which was pretty interesting. So why do the scale of neutrino masses and dark energy coincide? And what is the nature of neutrinos? So we'll try to use Swampland ideas to see how we can try to answer these questions. So I consider an extension of the standard model with 300 neutrinos. And if neutrinos are Dirac particles, then we will have 12 light degrees of freedom. If they're Majorana particles, then we will have somewhere between 6 and 12 light degrees of freedom, depending on how large their Majorana mass is. And we will see that seesaw scenarios where the Majorana mass is much larger than the Dirac mass lead to inconsistencies with several Swampland conjectures. So please, can you go to the next slide? So in order to do that, we consider circular compactification of the standard model and require that they should fall in the landscape. We check the conjectures through the effective potential of the radion. And this potential will have a term coming from the dimensional reduction of the cosmological constant, plus some quantum corrections, which are simply the dimensional reduction of the Casimir energy of each of the particles in the spectrum. And since we will focus on the infrared, we will need only to consider neutrinos. Can you please go to the next slide? So the first conjecture that was already considered in these papers in the literature, it tells you that non-supersymmetric ADS vacua should at best be metastable. And this effective potential in 3 dimensions has anti-de Sitter vacua. So if we assume that they are stable, then they should be avoided. And this can be this can be done if neutrinos are Dirac or pseudo-Dirac, and if their masses are smaller than the cosmological constant. But we need to assume that they are stable, and this requires UV information. So the idea of my talk today is to check other Swampland conjectures which require only infrared information. And if we go to the next slide, the conjecture that we consider is the anti-de Sitter distance conjecture, which tells you that as the cosmological constant goes to 0, a tower of states is expected to become light with a certain power alpha of the cosmological constant. And this vacua that I was talking about before, they depend on the masses of the neutrinos. So according to the conjecture, if in a certain direction of field space, so we can think perhaps we're changing the Vafa of the Higgs or the Yukawa, so that the standard model is actually part of some scanning, then if the cosmological constant in 3 dimensions so goes to 0, then some tower of states should become light. And if we go to the next slide, there we have a plot where this effective potential is shown for several values of the lightest neutrino mass. So we consider in this figure normal hierarchy, normal order in Dirac neutrinos, and that the lightest neutrino mass is between 9 millielectron volts and 6 millielectron volts, as you can see in the figure, and the potential goes from anti-de Sitter to Minkowski and to de Sitter. So according to the conjecture, we should forbid this unless some tower becomes light. So the easiest solution is that this scanning is not possible because there is an upper bound on the mass of the lightest neutrino. The masses of the other neutrinos are fixed by the neutrino oscillation experiment. So in this case, we would obtain 7.7 millielectron volts as an upper bound. But then for this figure, I'm assuming that such a scanning exists and the cosmological constant is not affected by this scan. So if we go to the next slide, we consider a more general scanning where perhaps the cosmological constant changes as we change, say, the Vafa of the Higgs. Now, Festina Lente is a conjecture that was argued in the papers in the literature that requiring that large black holes should evaporate in the Sitter space. Every charged particle in the spectrum should have a mass which is larger than their charge times the cosmological constant. So now we can see that if we try to do a scanning where, say, the mass of the neutrinos and the electrons, so for example, changing the Vafa of the Higgs, then we could violate this bound if the cosmological constant does not change. In fact, it should change with a power alpha greater than 4. And in order to preserve the neutrinos are smaller than the cosmological constant, so that we don't generate anti-de Sitter vacua, the only possible scanning would be with alpha equals 4. So now if we go to my last slide, we sum the results very quickly. So we can avoid this dangerous vacua if the total mass of neutrinos is smaller than 0.7 electron volts, while the experimental bound is 0.12. So we are actually pretty close to experiment. Now the simplest seesaw scenario of why active neutrinos would seem inconsistent, since we need them to be Dirac. And a possible scanning arises where all of these 3 conjectures are consistent with alpha equals 4. And this arises the possibility that neutrinos are perhaps part of a tower, they predicted by the cosmological constant. And in any sense, it is interesting to end with the question that perhaps quantum gravity provides a deeper explanation of why neutrinos are so light. Thank you.
Okay, so thank you, Eduardo. Any question? So Sayanton is asking how the neutrino mass constraints directly omega nu. Otherwise, can we measure that in observation?
How the neutrino mass constraints? So these bounds come from cosmology, and we only put bounds on the total scale. So we put bounds on the lightest neutrino mass, and the other neutrinos we fix their mass differences using neutrino oscillations. So there's only one parameter that we can change, which is the total scale. I hope that answers your question.
Okay. Any other question? So if not, let's thank Eduardo again. And let's move on to the next talk, who is by Jonah Coder-Flam from Chicago. Is going to tell us about distinguishing random states and black holes.
Thank you. Yeah, I would like to thank the organizers for the opportunity to speak today. This work is based on a paper that I wrote earlier this year and a follow-up that will appear shortly with Vladimir Narok-Lansky and Shinsei Ryu. Next slide, please. So Hawking told us that black holes will radiate thermal radiation. This is a breakdown of quantum mechanics, as it implies that different black hole microstates with the same thermodynamic parameters will evolve to the same final state. The question I address in this work is, how can we distinguish different black hole microstates when we only have access to the Hawking radiation? And this will probe physics beyond the page curve for the von Neumann entropy. Next slide. In quantum information theory, this problem goes under the name of quantum hypothesis testing. How well can we distinguish two states, rho and sigma, using a quantum measurement? For a given measurement, we conclude that we have state rho if we get measurement outcome corresponding to A, and we'll get sigma otherwise. There are two types of errors that can arise, concluding that we have state sigma when we really have state rho, and vice versa. So we seek to optimize our quantum measurement to minimize these errors. Different distinguishability measures, such as the trace distance, quantify the effectiveness of this optimal measurement. Next slide, please. So here I study a different distinguishability measure called the Petz-Renyi relative entropy, which quantifies the rate at which states can be distinguished as one is given more copies of the system. Using the replica trick, we can compute the Petz-Renyi relative entropy for mixed states independently drawn from the Wishart ensemble. The computation boils down to a particular sum over the permutation group and can be exactly evaluated at large N using combinatorics of non-crossing partitions. In particular, representing rhos as black dots and the sigmas as red dots, the dominant permutations in the sum are those that are both planar and the ones that do not connect the black and red dots. This leads to a closed form expression and depending on the relative Hilbert space dimensions of the subsystems. Next slide, please. So using these techniques, we're able to derive page curves for a large variety of distinguishability measures. As illustrative examples, I have shown the quantum relative entropy, the Chernoff distance, and the fidelity. As you can see, the relative entropy is particularly simple. Next slide, please. So we now study the West Coast model of black hole evaporation, which consists of JT gravity decorated with end-of-world brains with many flavors. We can take two different evaporating black holes in this toy model with the same entropy, and we compute the relative entropy between the states of the Hawking radiation. From the gravitational path integral, we find that the relevant configurations are replica wormholes that exactly coincide with the ones that we found for the Haar random states, namely the planar replica wormholes that do not connect end-of-world brains of one state with the other. Next slide, please. So these calculations imply that prior to the page time, the microstates are non-perturbatively distinguishable. An observer needs an exponentially large number of copies of the Hawking radiation in order to reliably distinguish the black hole microstates. But after the page time, an observer only needs a single copy of the radiation to reliably distinguish microstates, though such a measurement will be very complex. And had we not included replica wormholes in the gravitational path integral, we would have found that all relative entropies are zero at all times, implying information loss. Next slide, please. So I'll leave you with an advertisement to some other results from these papers. So beyond the measures already shown, we also compute the sandwiched Renyi relative entropy and the trace distance. We studied distinguishability of static black hole microstates in ADS-CFT when one has access only to a subset of the boundary data, finding corrections to the JLMS formula. And we generalized this to generic random tensor networks using flow network techniques. And finally, we established subsystem eigenstate thermalization for a large class of chaotic systems, including holographic CFTs in all dimensions. Thank you.
Okay, thank you very much, Jonah. And so there's already a couple of questions also by Sayantan So could you please elaborate on how combinatorics play a crucial role in the replica trick?
Yeah, so this is the this is what happens when you average over the Haar measure. So the first calculation we did was taking random states drawn from the Haar measure, or when you trace out a subsystem, this is the Wishart ensemble. And so this is standard connections between permutations and random matrix theory. And then the same kind of structures show up in the gravity due to the different ways that the replicas in gravity can connect. So there's a connection between these Haar random states and these replica wormholes.
He's also asking, could you please also comment on P of M, particularly why is it necessary in this context?
So what I wanted to do was say you're given the state of the radiation, and you're given that quantum state, and you want to determine what state it's in. And so what we're allowed to do in general is apply any positive operator value measurement. And so, yeah, that's how we determine what state we have. I'm not sure if that was exactly the answer, or the answer is exactly the question now.
Okay, so thanks. So let's see if there's any other question. Okay, we can maybe discuss later at the end of the Gong show if you want. Okay, so if there's no other questions, so let's thank Jonah again. And so let's move to the next talk by Erez Urbach from Weizmann, who will tell us about the entanglement entropy of typical pure states and replica wormholes. Erez, are you there? Erez? Okay.
Sorry, can you hear me?
Yes. Okay. Hi.
Okay. Hi. Sorry.
Good.
Hi. Yeah.
Yeah. You have 5 minutes.
Great. Next slide, please. So, yes. So we are considering a two-dimensional QFT on a circle, and in this theory, we will consider the von Neumann entanglement entropy on an interval A between 0 and phi, where phi is the angular coordinate on the circle, and we'll consider the entropy for pure typical states. So for pure typical states, you expect a page curve in the von Neumann entropy as function of phi, as you can see in the bottom right here. And by that, I don't mean that we have a black hole or radiation, just that the von Neumann entropy as a function of phi has a linear increase and then a linear decrease when the interval reach half the system size. We will reproduce this page curve for the average von Neumann entropy. And by average, I mean an average over a specific ensemble of high energy states with typical energy 1 over beta that we'll assume to be larger than 1. Next slide, please. Thanks. So first, a reminder, if you want to ask about the interval entanglement entropy for the thermal density matrix, then the replica trick instructs you to calculate the path integral over the following geometry of n tori with a replicated line between them, between 0 and phi. This is what you see on the top here. And if you further want to use the holographic dictionary, then you're instructed to find a gravity solution that its boundary is the geometry I was just describing. So let me describe the solution. If you take one of the tori here and slice it in the middle, you get a filled ring that I drawn below. So this is a black hole solution, and the black hole, the Euclidean black hole horizon is the dashed black circle you see in the middle. And from the boundary, you have the replicated line between 0 and phi that you need to extend into the bulk into a replicated surface that I drawn in blue. And as a result, you get that the von Neumann entropy eventually is proportional to the length of the boundary of this replicated surface, what I called x in the picture. In this case, the length of this x is, as you can see from the picture, because the replicated surface touches the horizon, its length is proportional to phi, and you get that the thermal von Neumann entropy as function of phi is linearly proportional to phi. This is what you see on the right. Next slide, please. Now, moving to the pure state, for a specific ensemble of pure states, you can show that the average entropy is given by similar path integral after you use the CFT replica trick. The difference is as follows. You again have n different tori and a replicated line between them, but now you need to further identify the n inner circles that are drawn here as a blue dashed line. So you have for each replica this circle, and in the path integral for the field, you need to constrain the fields such that the value of the field is going to be equal on all these circles. So you can think about it as some kind of path integral on singular geometry. Next slide, please. Given this path integral over singular geometry, you can now ask its value using the same holographic dictionary. Only now, because you have this singular boundary condition at this inner circle, you're allowed to have two different types of solutions. The first type of solution is the same thermal solution that you saw before, where the replicated line from the boundary is extended only up to the Euclidean horizon. This is what you see on the left. And as we just described, it gives an increasing entropy. But because we have this weird boundary condition, you also have another solution. This is what you see on the right, where the replicated surface is extended inside the horizon up to the second boundary of your spatial slice. And this is because the other boundary in the middle, that's the blue circle, has this weird-looking singular geometry from the boundary perspective. You can call it a wormhole solution because at least when phi is very small, all the geometry behind the horizon is connected in non-trivial way through the replicas. And this, if you calculate it, you get that this saddle contributes a decreasing entropy, and as a result, you reproduce the page curve for the average von Neumann entropy, as you can see in the next slide, right? So this is the average von Neumann entropy that we got, where the thermal saddle contributes for short intervals, and the wormhole, what we call the wormhole solution, dominates at large intervals, and as a result, you get the curve that you expected from the CFT side. Let me just mention again that this is not an evaporation process of any black hole, but we calculate here is just the entanglement entropy on the CFT side. And secondly, we didn't use any kind of island formula to get the page curve. The two solutions were kind of RT solutions from the like old type, if you want, just coming from two different kind of boundary conditions from the CFT because of this singular geometry. Thank you.
Okay, thank you, Aras. Any question? So Sayantan is asking, instead of wormhole, if you have recently proposed hard wormhole scenarios, then how will you do the job? So wormhole without averaging gravity.
I'm not sure I understood the question. Are you asking how to see those solutions without averaging?
So Sayantan, if you want, you can just open your mic and ask the question in words.
Well, in any case, let me just say that I don't know how to get these solutions without the averaging I considered.
How do you do that?
Yeah, I got it. At the CFT side, you can do the replica trick for any density matrix period, even if it's not defined for a path integral. So in this case, we have a specific path integral formulation for the state. If you just perform the normal replica trick, you get a specific prescription of path integral to calculate, and this is what I showed you.
Okay. Any other question? So if not, let's thank Aras again. And so we move on to the next talk. Oops, sorry. Sorry, just a second. Oh. Okay, so the next talk is by Suman Kundu from Tata Institute of Fundamental Research. And he'll tell us about bounds on wedge growth of flat space scattering from bounds on chaos.
Hello.
Suman, thank you.
Okay. Hello, everyone. I have done this work in collaboration with Diksha Chandorkar, Subham Dattachaudhary, and Professor Siraj Minuwala. Next slide, please. So let's start. It's a very interesting problem to classify all possible consistent graviton S matrices. We already know many examples of consistent S matrices in string theory. Compactifications in various Calabi-Yau manifolds gives rise to different scattering amplitudes. This makes the classification problem very difficult to pursue. But if we consider G string goes to zero limit, then we see that all known different string theory answers reduces to only 3 possibilities. These are Einstein gravity, type 2 theory, and heterotic string theory. This gives a very good place to start the classification. And one can ask, how many consistent classical S matrices are there except these 3? Chaudhary and collaborators have conjectured that there are none except those 3 known examples. By classical, we mean the amplitude will have only pole type singularities. This is still a very ambitious statement to prove because we have to consider infinite number of spin exchanges. We can further restrict and say that the only consistent classical gravitational S matrix whose exchange poles are bounded in spin is the Einstein S matrix. Next slide, please. In D less than equal to 6, this conjecture is indeed true, provided the S matrix will have only finite number of poles and it satisfies a physically motivated constraint on S matrix in Regge limit. This constraint is named as classical Regge growth conjecture or CRJ conjecture. I'll briefly mention the statement. It says the S matrix of a consistent classical theory never grows faster than S square at fixed T. But is this CRJ conjecture true? We have given a clear argument for CRJ conjecture using the bound on chaos and ADS-CFT for contact interactions of spinning particles. Next slide, please. In this work, we have considered a 4-point function of massless spinning particles in ADS. In this picture, you can see 4 insertion points P1 and P3 below at time tau, P2 and P4 above at an angle theta. These are the only parameters in the problem. As we change tau from pi to 0, it explores total 3 different causal configurations. Next slide, please. When tau starts from pi, it is in the Euclidean configuration. Once tau crosses pi minus theta, it enters causally Regge configuration where chaos bound applies. It says the normalized boundary correlator cannot grow faster than 1 by theta square in small theta limit. Finally, when tau is less than theta, it enters the causally scattering set where actual scattering can take place in the bulk and we get a bulk point singularity. Here we have identified the coefficient of bulk point singularity to the flat space S matrix. This is a typical equation for various spinning cases. It was done for scalars before. We have extended it for photons and gravitons. The rho divergence shown in red is the bulk point singularity. In Regge limit, sigma is taken to 0 and determines the Regge behavior. S tilde of omega shown in blue is the flat space S matrix in Regge limit of the same interaction. Next slide, please. In sigma goes to 0 limit, the same correlator takes this form shown in the box. It says the leading term sigma scaling is totally decoupled from the function of rho, and the sigma behavior doesn't change with the causal structure, which effectively determines the Regge scaling. Now all we need to do is prove that the function h of rho is an analytic function of rho extended over 2 configurations. The analytic continuation contour is shown in the figure. The above and the below part of the contour is in the Regge set and scattering set respectively. Now we got something nice. 2 configurations are related by an analytic continuation. This implies the function of rho cannot suddenly become entirely 0 in the scattering set if it is not 0 in the Regge set. This relates chaos bound in Regge set to the CRJ bound on flat space S matrix in scattering set. So to summarize what we have achieved, well, first we have derived a relation between leading rho singularity in ADS correlator and a flat space S matrix for spin 1 and spin 2. And second, we have proved that if chaos bound is true in Regge set, then CRJ bound is also true for in scattering set for any contact interactions. Next slide, please. We certainly have some limitations in our calculation. Since we did this calculation only for contact interactions, it is important to prove the CRG bound also for exchange diagrams. We have taken the flat space limit of ADS and used ADS CFT to show the CRG conjecture in the bulk. It would be very satisfying to get direct bulk argument for the CRG conjecture without use of any ADS CFT. I'll stop here. Thank you for your attention.
So thank you very much, Suman. Okay, so we have a question again by Sayantan. My very basic question is, what do we mean or understand from chaotic S matrix? Is this completely coming from a non-perturbative calculation, or so?
No, we are totally doing a perturbative calculation, and we are just taking the leading. We are actually calculating a 4-point correlation function, and the 4-point correlation function is calculated only for in the tree level. So it is definitely perturbative. We are not considering any non-perturbative thing. But now, is that answer your question? Okay.
So we have a question from the institute.
Yes, my question. First of all, very interesting argument. Thank you. But it's not totally obvious to me that your calculation was only good for contact interactions, because even a non-contact interaction, except through the massless exchange possibly, involves only a limited length scale bounded by the Compton wavelength of the exchange particles. And in ADS, your infinity was infinitely far away. So I wonder if you didn't actually prove more than you claimed.
Okay, so we have done this calculation only for contact diagrams. You are asking what will happen if we do the exchange calculation, like?
Sorry, yes, I'm basically saying, I could be, of course, very likely totally wrong, but I thought that exchange of massive particles would not be much different from a contact coupling. Of course, exchange of massless particles is different, but I assume that you know what are the massless particles. So you hardly even have to analyze massless exchange separately.
Yes. So first I should say that we have not done the massless case. The massless, like the external particles are massless in our calculation, and we have only considered contact interaction. So both exchange and the massive case we have excluded, but I can. So in the massive case, the we are actually doing a very high energy calculation. So at very
sorry. When I said massless or massive, I meant for the exchanged particle. If you generalize from your contact calculation to an exchange, I'm very naive and perhaps completely wrong, but I would have thought that as long as the exchanged particle is massive, it wouldn't be much different from a contact interaction. Perhaps that's confused.
I see.
Of course, you could also worry about massless exchanges, but those are so limited that you would know what they are.
Yeah. If we do, definitely we will do the massive exchange also. But okay.
Okay.
Actually, I don't have clear argument for this. That what will happen if the exchange particle is massive.
Okay, maybe we can
no, right now
table this discussion for later. Okay, so let's thank Suman again.
Okay.
Thank you very much. And so let's move to the next talk by Ahmadullah Zayed from the Indian Institute of Science, who will tell us about quantum field theory and the Bieber-Bach conjecture. Ahmadullah, are you there?
Yes.
Okay.
Thank you everyone for being here. Thank you the organizers. So I'll be talking about quantum field theory and the Bieber-Bach conjecture. And this is based on these two work, one with Anindya Sinha and another is with Parthiv Haldar and Anindya Sinha. Next slide, please. So if a function f of z is a univalent and we can normalize it such that its Taylor coefficient of z is equals to 1, then other Taylor coefficients that bn, if it's univalent, then its absolute value is bounded by bn is bounded by n. Absolute value of bn is bounded by n. And if f of z is a univalent function, then absolute value of this function is also bounded from two sides. And a univalent function is a function that is in a domain, it's a holomorphic and one-to-one. Next slide, please. So we are going to relate this univalent function to the scattering amplitudes. So from fully crossing symmetry, one can expand the amplitude in powers of around x equals to 0, y equals to 0, where x and y are the crossing symmetry combination of the Mandel-Stem invariants. X is the quadratic and y is the cubic Mandel-Stem invariants. And these W's are the Wilson coefficients. And we parameterize this Mandel-Stem invariants S and T as a function of Z and A, such that we can write this X and Y in this fashion. And now our amplitude is a function of A and Z. And we expand the amplitude around Z equals to 0. And Taylor coefficients are given by this alpha n, a to the power 2n. And this alpha n and this Wilson coefficients are related by these equations. Next slide, please. And now for fully crossing symmetric amplitude, one can write down a fixed A dispersion relation for the amplitude. And dispersion relation is given by this, where A is the S-channel discontinuity and H is the kernel. And from H is basically fixed, and one can show that H is a univalent function. And one can show that for a certain range of A, this S-channel discontinuity is non-negative. And from this information, from this crossing symmetry and the unitarity, one can prove the following things. One of them is the Bavaria kind of bounds, that Taylor coefficients of this amplitude around Z equals to 0. This alpha n modulus of this alpha n is bounded by this n. And there is a two-sided bound on the amplitude, modulus of the amplitude. And for a small a, one can prove that the amplitude is itself a univalent function. Next slide. So from n equals to 2, that means the second Taylor coefficients, alpha 2, one can get the bounds on the Wilson coefficients. Here is the bound for the first Wilson coefficients, W01 and W10. Ratio of these two should be in between these two values. And the figure, you can see that this black dotted line are the bounds, and this all the colored dots are basically the Pioneer metrics obtained from the Pioneer metric bootstrap. They all actually satisfy these bounds. Next slide, please. So there is an ongoing work by Anindo and Prashant, which uses the theory of typically real univalent functions that gives very rigorous and tighter bounds on the Wilson coefficients. Here are some examples. The first column is using the analysis of typically real univalent functions, and second is using the SDPP. SDPP results, the lower bounds and the upper bounds. Thank you.
So thank you very much, Hamadullah. And so any question? Yeah, Sasha.
Yes, thanks for the talk. I wanted to ask if your amplitude is not fully crossing symmetric, can you still apply these ideas?
Yes, in this upcoming work by Anindo and Prashant, they are actually trying to work with the two-channel symmetry, and still you can get. There you have to assume certain properties of the amplitude, that it should not grow faster than S. So you can then apply this same instrumentation, and you can get the similar kind of bounds. And amplitude is still univalent. You can show this bounds. Yeah, that's possible. Using only two-channel symmetry is possible.
Any other question?
I have another question, maybe also.
Sure.
Can you apply these ideas to CFTs? And do you know any examples of CFT correlators or explicit scattering amplitudes which you know are univalent?
Yeah, we can. In Mellin space, you can apply these techniques, and similar story goes there. And we had some initial observations that 2D Ising model Mellin amplitudes actually obeys all these bounds, yeah, as well as 3D Ising models. Yeah.
Thanks.
Okay, good. If there's no other question, let's thank Hamadullah again. And thank you. So, and let's move to the next speaker, who is Shruti Narayanan from Harvard. And she'll tell us about state operator correspondence in celestial conformal field theory. Are you there?
Yes, I'm here.
Hi.
Can you hear me?
Sure, yes.
Okay, great. Thanks to the organizers for this opportunity to speak. I'm going to be talking about some work done in collaboration with Aaron Crawley, Noel Miller, and Andy Streminder. Next slide, please. So four-dimensional Lorentz symmetries in the bulk are manifest as two-dimensional conformal symmetries on the boundary, which allows us to recast four-dimensional S-matrix elements as two-dimensional conformal correlators in what we call the celestial conformal field theory that lives on the boundary sphere. And operators in the CCFT correspond, therefore, to both incoming and outgoing bulk fields that puncture the celestial sphere at a given point. So in this talk, I'll try to find a bulk product that makes sense as a CFT two-point function and use the state operator correspondence to define operators in the CFT. I'll then apply the BPZ construction to this two-point function to get an inner product on 2D states and discuss the implications for 2D versus 4D scattering. Next slide, please. So we start by considering solutions to the free 4D scalar massless wave equation, and we know that it admits a conserved current J mu, which allows us to construct a symplectic product. But we could also modify solutions to the wave equation. For example, if we complex conjugate one of the fields, then it gives us the usual Klein-Gordon inner product that's used in particular in the normalization of conformal primary wave functions. And conformal primary wave functions have been very useful because they allow us to explicitly transform from a momentum basis to a conformal primary basis, which allows us to explicitly see the connection between 4D S-matrix elements and 2D conformal correlators. In particular, for here, it's shown for massless scalars. This transformation is given by a Mellin transform. And one should note that analogous currents and products can be constructed for arbitrary spin, and what follows can also be done for massive fields. It just requires a more complicated integral transform. Next slide, please. Right, so one would assume that a bulk product between two conformal primary wave functions could be thought of as a transformed S-matrix element, so a CFT two-point function. However, when we actually calculate the Klein-Gordon inner product between two of these wave functions, we get a delta function in W1 and W2, which is not what you usually expect for a 2D CFT two-point function. Rather, we expect a power law. Additionally, the adjoint of the conformal generators, Ln, looks like minus Ln bar under the Klein-Gordon inner product. And this is another alien property that we experience via this inner product, as shown by this red alien in this box. And so we try to attempt to fix both of these things. In particular, if we want to fix the first problem, we can introduce the shadow transform, which has proven to be ubiquitous in discussions of celestial amplitudes. And in particular, it serves as a modification to this inner product where we shadow one of the fields in the symplectic product And it turns out that if we do that, we do actually get something that has the power law structure of a usual 2D CFD two-point function. Next slide, please. So now that we have something that looks like a 2D CFD two-point function, we can talk about the state operator correspondence. This is just done like it usually is in 2D CFT, except here what we have to do is we have to construct northern states and southern states. And this is important for our Hilbert space discussion that I'll end with. So northern state is a state that enters at the south pole of the past celestial sphere and exits at the north pole of the future celestial sphere. Similarly, a southern state, it moves in the opposite direction. In terms of a mode expansion, this means that a northern state is expanded around W equals 0, whereas a southern state is expanded around W equals infinity. And together, these two define the two different Hilbert spaces that we find on our celestial sphere. Next slide, please. So now that we have operators, we can take this shadow product, which looks like a 2D CFD two-point function. We can contour integrate appropriately to get a BPZ inner product between these two operators. And in particular, it has two properties that we normally expect in a 2D CFT inner product. It has, as shown in blue here, the constraint that the conformal weights of the two operators have to be the same, and also that we have the Kronecker delta function in the red box, which tells us that the adjoints of the operators are given by shadowed operators of the same conformal dimension. Okay, so this tells us that we need to not just consider unshadowed or shadowed fields in our Hilbert space in this CCFT, we actually have to consider some kind of combination of shadowed and unshadowed fields. Finally, if we take this inner product, we can compute that L in dagger is L minus N as one expects in a 2D CFT. So we've also fixed that problem alongside this one. Next slide, please. So this reformulates the scattering problem because in 4 dimensions, we usually have an in Hilbert space and an out Hilbert space where we have all of our states coming at scri minus and all of our states going out at scri plus. And the 4DS matrix is a map between these two spaces versus in 2 dimensions, we have our operators in the northern Hilbert space that correspond to both operators of ingoing and outgoing particles, as well as in the southern Hilbert space. And our 2D inner product actually maps between these two Hilbert spaces. So whereas the information that is contained in the 2D picture is the same as the information contained in the 4D picture, the organization of the data is slightly different, and hopefully we can learn something from that difference. Thank you.
Thank you very much, Suti. So any question?
Is this product positive?
Sorry?
Is it positive definite, the inner product you are defining?
Yeah, so that's a good question. Because it's constructed from the, if you consider positive frequency states, then yes, it's positive. But you can also consider negative frequency states, in which case it's negative definite. But it seems like that doesn't actually pose a huge problem in this picture because the same is true of the inner products between the conformal primary wave functions.
Any other question? So, okay, so if not, let's thank Suti again for the nice talk. And let's move on to the next talk by Akash Goel from Princeton, who will tell us about towards a string dual of SYK. Akash, are you there?
Yep. Can you hear me? Yep.
Yes. Okay, thank you.
Thank you for giving me the chance to speak here. So I will be describing this work with Herman Verlinde. Next slide, please. Next slide, please. Yep. So the SYK model is a model of interacting Majorana fermions. In particular, the Hamiltonian is described by a p fermion interaction term with couplings J that are drawn from a Gaussian random distribution. And the disorder averaged SYK model can be described in terms of an action that is just with bilocal fields G and sigma that live naturally on the torus. And in particular, in the double scaling limit, this action simplifies to a Lorentzian Liouville theory. And over the past few years, this model has been shown to be a very useful toy model, for instance, to study the physics of black holes. And that motivates us to try to embed this model within string theory. Next slide, please. The context in which we are going to be studying this problem is in minimal string theory, which Thomas reviewed this morning. So it's described by minimal matter coupled to Liouville gravity as well as ghosts. And the operators are in this theory are the physical tachyon operators, as well as the operators at ghost number 0, which generate the ground ring of the theory. And there are two types of branes. There are the continuous FZZT branes, which extend in the Liouville direction from the point of view of the target space and are labeled by the boundary cosmological constant, as well as the discrete ZZ branes. And these branes are known to live naturally on a semi-classical target space, which is a well-studied Riemann surface from the point of view of the spectral curve of the corresponding matrix model. So the matrix model in question is the two-matrix model, which is described by n by n matrices A and B, as well as potentials Vp and Vq that are polynomials of order P and Q respectively. And in order to make contact with the minimal string, one needs to tune these potentials to the P, Qth multicritical point in a double scaling limit. Next slide, please. It is also known how to insert FZZT branes from the point of view of the corresponding matrix model, namely by inserting these determinant operators. And if one inserts multiple determinant operators, if you insert multiple FZZT branes, we can introduce a matrix XQ that lives on this, the flavor space of the locations of these FZZT branes. And one can also trade off this determinant for an integral over complex fermions, where these fermions have an index that lives on the ZZ brane and another index that lives on the FZZT brane, so that you can think of these fermions as open strings that stretch between the two types of branes. So here's the construction. We will be considering the P,1 theory with QFZZT branes, which has this action. And in this case, it is easy to integrate out the degrees of freedom that live on the ZZ brane, namely the matrices A and B, and get an effective description in terms of the fermions. One can further use the scalar flavor map to introduce degrees of freedom that live purely on the FZZT brane. And this has been studied well in the double scaling limit and is known to be equivalent to the Kontsevich matrix integral. However, let me stress that in order to obtain our SYK phase, we are going to be focusing on the large Q limit. Next slide, please. So after integrating out the A and B fields, we obtain a matrix version of the SYK time. So now we need to introduce elements to make contact with the SYK time direction. And so to that end, let us introduce these matrices U and V that satisfy this algebra. U is the clock matrix, which is diagonal and whose elements are the qth roots of unity, and V is the shift matrix. So any Q by Q matrix G can be expanded in powers of U and V, and one can extract the coefficients of this expansion to build a function G of UV, whose Fourier coefficients are these coefficients in that expansion, and which lives naturally on the torus of period 2 pi. So under this map from Q plus Q matrices to functions on the torus, the matrix product maps to a star product, and the trace of the matrices maps to an integral over the coordinates on the torus. One can also extend this map to vectors, and one can also use these properties to carefully construct a matrix XQ such that it maps to a discretization of discretized derivative in the U direction in units of H bar. And it turns out that it's also important to construct in our construction to limit to modes of psi, which are integer multiples of square root Q in this expansion. Next slide, please. So after accounting for this subtlety, one obtains an action that takes this form. And if we assume that we can take a smooth continuum limit, namely the large Q limit or the H bar going to 0 limit, one can replace the star products in this action with the ordinary product of functions. And so we conclude with this phase diagram that we obtain, where we have an SYK-like physics in the regime that is dominated by the FZZT branes, and we have the minimal string phase in the large N limit. And let me also mention that in the double scaling limit of the SYK model, one can reduce this action to a sum over two Liouville theories with complex central charges that sum to 26. Thank you.
Thank you very much. Thank you very much, Akash. So questions? So there's already a couple of questions in the chat, but let's see if there's a live question. Okay, otherwise, so Sayantan is asking, if you fix the coupling J, then is it possible to find the string dual in that case?
Not that I know. So here we had the simple, the advantage of working with the disorder average theory is that you have a model that lives naturally in 2 dimensions. Right, so we had this map to the non-commutative torus. It seems a bit harder to get an effective description in terms of a particular realization of the SYK model. In particular, it seems that the string theory knows only about the disorder average and not a particular instance of the SYK model, at least in our construction.
Okay, so there's a question by Shiu.
Hi, what is the role of time in this duality?
So time, in what sense do you mean? So the time, we have an emergent time, right? So that comes from
one side,
from the Q, yeah, from the FZT space, yeah.
Sorry, from the FZT, how is time emergent?
So you should think of, so you should think of at finite Q, you should think of it, this model, the target space, as living on a discretization of the torus in units of h bar, where h bar is 2 pi over q. And as you take, and so this torus is the time cross time in SYK. So because you see that the SYK time is, the Euclidean time is periodic with period beta. So this 2-dimensional effective theory lives on the torus of beta cross beta, right? And once you go to the non-commutative torus and you take the Q to infinity limit, you get a continuum torus, which where the skew variable essentially transmutes to the continuous time variable in that case, which and this Q parameterizes the number of FCCT branes in the construction.
Thank you.
Okay, so thanks. So let's thank Akash again.
Thanks.
And now let's move on to the next speaker, Shenghao Zhong from Imperial, who will tell us about magnetic quivers and superconformal field theories. So Shenghao, are you there?
Yes, thank you for having me. Hi, I would like to talk about magnetic quivers and superconformal field theories. And this is based on a few works in collaboration with Antoine Bourget, Santiago Cabrera, Simone Giancomelli, Julius Grimminger, Amitan Hanani, Marcus Sperling, Gabby Zafir, and Anton Zayak. Next slide, please. So we are looking at 4dn equals 2 and 5dn equals 1 as CFDs. Now, these theories have a very rich vacuum structure, which makes it worthwhile to study the moduli space of vacua called the Higgs branch. However, the Higgs branch of these SCFTs can often be difficult to study directly. So here, we take a more indirect approach. For each 4dn equals 2 or 5dn equals 1 theory, we will try to find their corresponding magnetic quiver and study that object instead. So a magnetic quiver is defined as a 3dn equals 4 gauge theory whose Coulomb branch is the same as the Higgs branch of your 4D or 5D theory. Now, this makes the magnetic quiver a very nice object to study because in the last decade or so, there have been many new tools developed specifically to understand the Coulomb branch of 3dn equals 4 gauge theories. So now we're able to use these tools to study the Coulomb branch of the magnetic quiver and hence indirectly study the Higgs branch of your desired 4dn equals 2 or 5dn equals 1 SCFT. Now, the question is, given an SCFT, how do we find this corresponding magnetic quiver? Well, a natural way to do so is using a brane system. Next slide, please. So let's begin in 5D. Let's take a SU3 gauge theory with 6 flavors and 0 Chern-Simons level. and I take this gauge coupling to infinity so that I'm at the superconformal fixed point. Now, the brane system, which describes this SCFT, involves 5 branes and 7 branes. So on the left-hand side, we have the brane system. We have a circle with a cross, which represents 7 branes that stretches into your computer screen. And we have the different colored lines, which represents 5 branes stretched between the 7 branes and can move along them. So the position of the 5 branes along the 7 branes was then parameterized the Higgs branch of our SCFT. And from this brane system, I can immediately read off the corresponding 3D magnetic quiver. For example, the different stacked 5 branes will now correspond to different unitary gauge groups in the magnetic quiver. And the rank of the unitary gauge groups depends on how many 5 branes are stacked together. Next slide, please. So to summarize, the Higgs branch of this 5D n equals 1 theory is the same as the Coulomb branch of this 3D n equals 4 magnetic quiver, which we obtained using the brane system. Next slide, please. So now we can go one step further. We can take this 5D n equals 1 SCFT, compactifies on a circle with a Z2 twist. And this is known to produce a 4D n equals 2 SCFT with a C3A1 global symmetry. And we can repeat this procedure directly on the magnetic quiver. We take the magnetic quiver of the 5D theory and we identify a Z2 symmetry on the quiver and fold the legs along the symmetry. The resulting folded quiver will have non-simply laced edges represented by little arrows. And the Coulomb branch of this folded magnetic quiver is indeed the same as the Higgs branch of the 4D n equals 2 SCFT. And we can repeat this procedure by folding magnetic quivers of other 5D n equals 1 SCFTs. And this exercise allows us to find all the magnetic quivers corresponding to the classification of 4D n equals 2 rank 1 SCFTs. Next slide, please. So now that we have the magnetic quivers, we can use it to study the Higgs branch in more detail. For instance, we can explore the different phases of the Higgs branch, which at each phase, there's a different set of master states, and there's transitions between one phase and the other. So this information can be encoded in the phase diagram. So the Higgs branch phase diagram of our 5D n equals 1 and 4D n equals 2 theories are given on the right-hand side. The black dots represents the different phases, and the blue lines are the transitions from one phase to the other. And again, this phase diagram can be obtained directly from the magnetic quiver. So this uses a purely diagramical process called quiver subtraction, where you take the magnetic quiver, subtract a smaller quiver from it, and repeating this process will give you the phase diagram with all the phases and transitions, which nicely encodes this geometry of the Higgs branch. Thank you.
So thanks a lot. So any question for Zhenghao? Yeah, Arthur, please.
So can you get your magnetic quivers also by reducing your 5-dimensional theories to 3 dimensions and then just doing a mirror symmetry through the 3-dimensional brane constructions?
So, so from the 5D to the 4D, it was quite lucky that we can just fold the magnetic quivers and obtain the result. And we don't really have such an analogous procedure from 5D to 3D. So for example, the magnetic quivers, the Higgs branch of the magnetic quivers can't really compare to the Coulomb branch of the 4D or the 5D theories. So we don't have the exact 3D mirror symmetries yet. Thank you.
Any other question? Okay, so if not, let's thank Zhenghao again.
Thank you.
And let's move on to the last talk, which is going to be shared between Yangrui Hu and Hazel Mack from Brown. And they'll tell us about solving a 40-year-old problem, 11-dimensional superfields. So please.
Thank you. So hi, everyone. I'm Hazel.
Hi, I'm Yang Rui.
First, thanks to the organizer for giving us this opportunity to present our work. So today we are going to tell you a story about a very fundamental question in supersymmetry, that is, how to write an 11-dimensional superfield. This problem has been hanging around for 40 years, and last year we solved it. This is based on our series of work collaborated with Dreamgaze. Next slide, please. So the concept of superfield was introduced in 1974 by Salem and Strefty, and it was demonstrated in 4D. So a few years later, 11D onshore supergravity was constructed. One very natural question would be, what is the offshore version? Instead of irreducible supergravity, let us focus on the easier reducible supergravity, and one approach would utilize 11-dimensional unconstrained superfields. This leads us to ask, what are the component fields sitting in an 11-dimensional superfield? This very fundamental problem, however, has been left unsolved for 40 years. Last year, we decided to abandon the traditional gamma matrix method and invoke some Lie algebra techniques and also computational tools such as Liard and Susino mathematical packages. And for the very first time in history, the structures of 11D superfields were revealed. I will let Yang Wei to describe the setup of the problem. Next slide, please. Thanks. Let's start with the scalar superfield in 11 dimension under the superspace framework. Then a scalar superfield can be written in a schematic form on the screen via the theta expansion. So we have level 0 to level 32. Then since the component fields have to transform covariantly under the Lorentz group, then the question is how to decompose the red prefactors here into SO110 irreducible representations. And this question is highly non-trivial, not only since there are 2 to the 32 total degrees of freedom, and also if we construct them directly using the 1024 gamma matrices, we have to deal with tons of fierce identities. Even worse, at higher levels, there is no systematic way to write down Lorentz covariant theta monomials. So this sounds like a dead end, right? No. 2 observations allow us to get around these issues, and Hazel will show you the first one. Next slide, please. So the first observation goes as follows. Grassmann coordinates anti-compute, so a product of them will be totally anti-symmetric. Since the total degrees of freedom of certain tensors with certain symmetries can be described by Young tableaus, we could represent level n as a column of n boxes. But Young tableau has another meaning. Any Young tableau can be mapped bijectively to a SUN irreducible representation. Therefore, we could interpret each level as a SU32 irreducible representation. And this sets the stage for Yang Wei to show you the magic. Next slide. Well, based on this observation, the question reduced to how to project a SU32 irrep into a direct sum of SO110 irreps. It happens that SO110 is a subalgebra of SU32. So branching rules, by definition, give us the answer. Here are 2 examples for quadratic and cubic levels. Both Liard and Susino package can carry out these calculations. And the numbers here are dimensions of the irreps. In fact, we not only know the dimensions, there is a 1-to-1 correspondence between irreps and the field variables. From their Dinkin labels and other related branching rules, we actually know index structures and irreducible conditions of all corresponding field variables. This is achieved by introducing bosonic and spinorian Young tableaus and using some graphical rules to visualize the branching rules. And you can check this paper for details. Next slide, please. So with all these tools, we find the Lorentz descriptions of all the component fields of an 11-dimensional scalar superfield. So here is an identical graph. Each node is a SO110 irreducible representation, and the number in the node is the dimension of that irrep. And as Yang just mentioned, we can translate them to Dinkin labels, Young tableaus, and also index notations. White nodes are bosons and black nodes are fermions, and the black links between them are transformation laws. So from bottom to top, we have the component fields from level 0 to level 32, and they are symmetric about level 16. So it will form some kind of diamond shape. We only show up to level 5 due to limited space. So do you think we only know the component contents of the 11-dimensional scalar superfield? The answer is no, because by using Bernoulli's method, we can actually obtain the component contents of any superfield by doing the tensor product of the scalar superfield with the irreducible representation of that index structure. Next slide, please. Now let's think about the supergravity. In the Nordstrom limit, we only consider the conformal compensator V, the scalar superfield. So the complete field content of the 11D scalar superfield that Hazel just showed you provides a clear picture of the Nordstrom supergravity. Also, we found possible embeddings for conformal graviton, gravitino, as well as 3 forms occur in the middle levels of the scalar superfield. Moreover, if we write the scalar superfield as a derivative of V alpha and use the Bernoulli approach, we found that V alpha actually contains the complete component field of the Poincare bind at level 17. These findings highly suggest that the scalar superfield plays the role as both conformal compensator and semi-prepotentials. And the superfield V alpha is the prepotential candidate taking a surprisingly simple form. With all of that, we finally reach a possible starting point of writing an 11D superfield supergravity theory, which potentially enables the study of M-theory corrections and beyond. This is all we want to present today, and thank you very much. Thank you.
So thank you. So there's a question by Shiu.
Hi. So there's a 2009 work by Martin Sedewall in which he constructed a fully supersymmetric off-shell action for 11D supergravity using pure spinor superspace. Can you comment on the connection between that and your work?
Yes. So their work is actually kind of orthogonal to our approach. Since we starting from the unconstrained superfield constructions, so we do not impose any constraint like the pure spinor approach and other approach like using the studying the supergeometry perspective. So we kind of orthogonal.
But I mean, is there some disadvantage of Sedewall's approach that your approach would overcome? I mean, what is the problem with that pure spinor superspace formulation?
So like so for the pure spinor, you have to impose the pure spinor condition for the superspace, right?
No, that's just constraint on the variables. It's like harmonic superspace. Yes. I mean that's right. But the pure spinor square fields are perfectly well defined. I mean, of course you can have constraint variables.
I mean, yes, you can proceed like this problem by that approach. We don't want to consider that kind of constraint, since we want to understand this problem from the inside variables like the prepotentials, and then we go to the construct the like the covariant derivatives and calculate the field strengths, and then to go to the supergravity. So we use another approach, but yes, you can use the pure spinor to do some work in that direction.
So Nathan.
The advantage of Martin's work is that he has an action. Do you have a proposed action for your superfields?
That's a very good question. Yes, go ahead, Hazel.
Yeah, so we actually follow the spirit of Bernoulli, who like in 1977, he have written down a 4D supergravity theory which is reducible, and then like he takes a factor superfield and tensor product with a factor, so they get a graviton that is reducible and is unconstrained, and is he didn't write down the action. So in our approach, we also didn't write down an action. And I think to achieve that, maybe the first thing that we want to do is to take this unconstrained, this result is actually unconstrained superfield, and actually put some constraint in, and then make it to irreducible supergravity, and then we can think about action. Yeah.
Do you know the dimension of your scalar in this superfield?
Sorry, like we are in 11 dimensions, so yeah.
So it's a very negative dimensional scalar. I guess your graviton is at level 16, so maybe it's -8 or something like that, the dimension.
Yeah, yeah, maybe it would be a little negative, but because we haven't actually written down the action, and like for the comment that I just mentioned, like M theory correction and stuff, we are thinking of doing it in like using equation of motion, like Bianchi identities instead of like going to action. So
yes, if you count the dimension like in the action perspective, yes, maybe some of the component fields will carry the negative dimensions, and even it's impossible to write down the Lagrangian. But the point is that for now, we didn't impose any constraint. And if we go that direction and try to write down the action, we have to impose some constraint to like make the superspace smaller to write the proper action. Yeah.
Thank you.
Okay, so thank you. So let's thank Yang-Rui and Hazel again, and all other speakers of today's session.
Thank you.
And I also wanted to remind you that there is a Slack channel for the Gong show on Slack, so that there were a few questions that were left maybe unasked and unanswered, and you can maybe continue the discussion there if you want. Otherwise, we adjourn to tomorrow morning or afternoon, depending. Okay, so thank you all, and see you tomorrow.
Thank you.
Bye-bye.
Hi, Diego. Just want to say hi. We haven't had the chance to say hi to each other.
Hi, Gary. Hi, how are you?
Thanks.
Good.